Hello, everyone, and welcome back to day 2 of our 2023 Alaska Sustainable Energy Conference virtual workshop series, Carbon Capture Sequestration, the Myth and the Reality, sponsored by the University of Alaska Fairbanks and the Alaska Center for Energy and Power, ACEP. I'm Frank Pasphan, an affiliate professor at the University of Alaska Fairbanks for carbon capture, and I'll be your MC for the second day of this event. Thank you for joining us. Introducing myself, I'm a born and raised Alaskan and went to the University of Alaska Fairbanks in petroleum engineering. I worked 36 years in the oil and gas industry as an engineer, coach, and manager in various locations, primarily here in Alaska and also in Indonesia and Texas. I joined the University of Alaska Fairbanks in 2021 specifically to research CCUS and have joined to lead a statewide CCUS work group that shares knowledge and supports commercial CCUS project development. CCUS, carbon capture, use, and sequestration, is a way to ensure that Alaska has a means to decarbonize its energy production value chain. So our work group meets regularly to discuss carbon capture projects here in Alaska. We meet both online and at the BP Energy Center in Midtown Anchorage, and it's typically on a monthly basis. So if you're interested in CCUS and would like to join the work group, you can visit our website at ine.uaf.edu/carbon or send an email to ccusalaska@gmail.com. So it's interesting to note that CCUS has gotten a lot of attention lately. This workshop is just one of the many ways that public engagement has begun. And our CCUS work group actually supported the state of Alaska in its development of the legal and regulatory framework for carbon storage. There's 2 bills with the state legislature now, Senate Bill 49 and House Bill 50. And these were introduced by the governor to establish the legal framework for carbon storage, including, for example, pore space leasing, which enables that process. And if you're interested, you can follow along the legislative process. And I'm sure your legislatures would love to hear from you if you would like to share your viewpoint on those bills. You can search for SB 49 or HB 50, and there's a wealth of testimony and comments. So moving into the workshop, as Haley shared yesterday, this a series of 3 virtual workshops is being held monthly as 2 half-day Zoom sessions, which are free of charge, and they're leading up to the Alaska Sustainable Energy Conference, which is happening in person May 22nd through May 25th at the Dena'ina Energy Center in Anchorage, Alaska. There should be a link to that event in the chat. We kicked off with low carbon energy transitions, lessons learned from global pathfinders last month, and we will close out the series with energy storage beyond lithium-ion batteries in May. If you're interested in checking those out, recordings of each virtual workshop are available at the Alaska Sustainable Energy Conference website, which is in the link www.alaskasustainableenergy.com. Looking forward to our time together today. Please see our agenda up on the screen, and this will review our daily program. After this welcome, we'll hear from Iceland as a pioneer in CCS technologies around 8:50 a.m. this morning, and then followed by the Sask Power Boundary Dam 3 project. This is the first power station in the world to implement CCS technology, and they have a tremendous body of knowledge that's been developed through that experience. At 10:10 a.m., we'll be taking a break and join back in at 10:25 to hear from some folks in Scotland on Project Acorn, growing the UK's decarbonized future, followed by, back here in Alaska at 11 a.m., SINGSA gas storage and transport in Alaska. We selected the SINGSA project because it's an actual gas injection project going on here in the state. It's central importance to the smooth operation of our natural gas distribution system. and it's an ongoing project here in Alaska that has gas storage, which is a strong analog to carbon capture and storage. And then we close out at 11:35 a.m. with the final presentation, opportunities for CCUS and the coal sector in Alaska. And wrapping up the session, we should have closing remarks starting at 12:05 p.m. Alaska time. So we'll look forward to that. We have a tremendous amount of information. And I would like to recognize yesterday's presentations and appreciate Haley Payne from the DNR and her excellent hosting and emceeing of that workshop yesterday. And those presentations will be online on for those who missed that or would like to review those materials. So each of these presentations will be followed by a Q&A between our attendees and presenters. So be sure to enter your comments and the questions in the chat. The chat log is available. It should be on the bottom of your screen. And if you want to put any questions in, the moderator will review those and share those with the presenter. And that's an important part of this conversation. So before we actually get started with the actual presentations, we're going to kick off with a couple of polls. To participate in those polls from your computer, you can enter www.slido.com, and you can see the code that's there on the screen. Or you can take your smartphone and use it and scan the QR code. The link's on the screen now, and we recommend Google Chrome as for best results. So our first poll question today is actually a repeat of a question that we asked you yesterday, just kind of a pulse check to see what the participants' viewpoints are here. Question is, what are your thoughts about CCUS activities taking place in Alaska? Supportive, mixed, undecided, and opposed. It looks like it's generally supportive, around 60%. View this as could be an exciting new opportunity for the state's economy and environment, with 30% mixed, some positive applications, but uncertainty exists. 13% undecided, don't know enough yet to decide either way, and that's excellent. We hope to provide additional information today and look forward to your questions, comments, and concerns. Opposed, this seems like a dangerous idea and do not want to see it in Alaska. All right. Thank you for that. We'll move on to our next engagement poll, Slido question 2. And this is really looking back at yesterday's workshop. Let's see, we've got a few more people still providing input on question 1. So thank you for that. Moving on to question 2. How did yesterday's workshop change your viewpoint on carbon capture and storage? Are you more supportive, no change, less supportive, or not applicable? Did not attend yesterday's session? Well, that's great. It looks like a full third are more supportive, and that's interesting. No change, 65%. So and 5% did not attend yesterday's session. Thank you for joining us today. That's great that you're here, and we'll have some great information. And as I shared before, we do have recordings of yesterday's presentations and the materials, which were prepared from really experts around the world tremendous set of presenters yesterday. Okay, looks like that's pretty well stabilized. So about 60% no change, more supportive, 33%, and interestingly, 0% less supportive. So learning about this in some detail was quite useful. Great, thank you. I think we're ready to move on to our third question, and this is our final poll question. And this is really kind of looking forward. Maybe some of the presenters could fold this into their discussions today. And the question is an open text question. What else would you like to learn about CCS? There's only a limited amount of time in these two-day, half-day workshop sessions. And so this would be great information and perhaps information we could use to inform some of the activities at the Sustainable Energy Conference coming up in the end of May. As you can see on the screen, these are anonymous polls, so feel free to share, and knowing that it won't be attributable. Economics and costs. What about direct air capture? What types of materials for CO2 transport? What is recycling of carbon in Europe rather than storage? What does the value chain look like in Alaska for CCUS? How long would it take in the Cook Inlet? More on the regulatory framework. How can I get more involved in Alaska? One way is to send an email to ccusalaska@gmail.com to join our CCUS work group. Where will we get CO2 for injection without a significant manufacturing base in Alaska? To address that, some of the conversations today will speak directly to that. In fact, the last one from Usabelli Coal Mine will talk about the coal-fired plants in operation in the interior. Are there research opportunities for university faculty and students? Opportunities to connect CO2 sources with end users. Great. Relevant energy costs. Great questions. We have 3 participants still typing. What's the timeline to get it implemented? International collaboration on CCUS. That's a great one. This is a new technology, and learning from others and their experiences is a lot about what today is all about. So great questions. And life cycle analysis and CO2 capture technologies. Great, thank you for that. Thanks for participating in this morning's polls. I guess a couple of housekeeping items. We'd like for you to please introduce yourself in the chat. Let us know your name and the organization you're from. And that chat box is the same place where you'll ask any questions you might have or add any comments. Don't use the Q&A thing. Just go to the chat within Zoom, and that's a great spot. So some other housekeeping. During this workshop, attendees will be muted, and that's so you can submit questions and comments in the chat feature. The moderators read the questions to the panelists at the end of each discussion. And if you have any troubles with audio or viewing, please chat to event support for assistance. They're online and super helpful, able to resolve questions or any issues. So a recording of this workshop will be available at the www.alaskasustainableenergy.com. shortly. So if you have to step away or want to rewatch or share a presentation with friends, family, neighbors, you'll be able to do it from that site. Excellent. So with that, and thanks everyone for putting your names and affiliations in the chat. We're going to move into today's first presentation. And please join me in welcoming our first moderator, Gwen Holdman. Gwen is the Associate Vice Chancellor for Research, Innovation, and Industry Partnerships at the University of Alaska Fairbanks. Gwen, will you take it from here?
So thank you, Frank. I think that was really great to see all of those questions about what people are curious about with CCUS technology. And one of the questions I saw in there was about direct air capture. And for this first session today, we're going to travel to the other side of the Arctic to learn a little bit more about what Iceland has been doing with CCS in the CCS space, and specifically the development of DAC, direct air capture technologies. During the Q&A yesterday with David Lepane, we got a little bit of a preview of Iceland's sort of unique geologic setting and the opportunity that presents for CCS. And I'm sure that we're going to learn a little bit more about that from our next couple of speakers. I should mention that the University of Alaska Fairbanks, Alaska Center for Energy and Power, and our Alaska Blue Economy Center have been developing a really close partnership with Iceland that we've actually been sort of expanding over a number of years. And that covers a lot of different technologies, not just the CCS space, but energy more broadly and the blue economy. And so we actually have a new research professional who's based in Iceland full-time and co-located with Iceland's ocean cluster. His name is Erlinger Gudleifsson, and so he's actually helped us coordinate the speakers for this panel. And he'll be at the Alaska Sustainable Energy Conference as well. And so we're going to start today with Ragna Bjork Bragadóttir, the Innovation Project Manager for Carbfix, who's giving up her evening to spend time with us in what is morning here in Alaska. And so I've had a chance to visit the Carbfix headquarters many years ago as part of a tour of the geothermal park and sort of this cascading utilization of geothermal industry. And I saw the new construction at the Hellishady power plant a few months back, and I'm really excited to learn a little bit more about your future plans. So thank you for joining us, Ragna. I'm going to turn it over to you.
Yeah, thank you for having me. It's a pleasure. Yeah, so Ragna Björk Bragadóttir is my name. It's not easy to pronounce, so yeah, Icelandic names. So I am the Innovation Project Manager for Carbfix, which is a really small but growing company here in Iceland, and we are doing carbon capture, mineralization, and storage. So yeah, this is what we're doing. We are turning CO2 into stone. Have been since 2012. So yeah, my company Carbfix. So just to start with just a little bit of a background. So why we are really doing what we're doing. So it is completely clear that the climate goals will not be met without widespread carbon capture and storage. And I hope you all know this. So CCS, or carbon capture and storage, are estimated to have to remove or emission reduction of 115 gigatons before 2060, which is a lot. So imagine you're standing next to this amazing waterfall in Iceland, just to bring a little bit of Icelandic nature to you. This is Gullfoss, one of our most visited waterfall in Iceland. Quite impressive. Now imagine if we turned all this water into CO2. So then if, according to these 115 gigatons needed before 2060, this is the amount we need to inject into the subsurface every second of every day until 2060 to meet these 150 gigatons. So this is quite a lot. So let that sink in. So there's a lot for everyone in this industry. Now more pictures from Iceland, which in most presentations I give are always quite impressive. However, I have been to Alaska, so you might not be so easily impressed, but hopefully a little bit. This is Eyjafjallajökull. You might remember the havoc it made when it erupted in 2010 and grounded all air traffic in Europe and in Northern Europe. However, I wrote there the climate-friendly volcano because by doing that, actually the amount of CO2 that was emitted from the volcano was a lot less than was estimated from all this air traffic that was grounded. So in reality, a little bit climate-friendly, which is not usual for volcanoes. Yeah, but what are we doing at Carfix? We are doing things a little bit different from what you tend to think about when you think about CCS. Because our work is more carbon capture and mineralization and storage, where we turn CO2 into carbonates underground in less than 2 years. And this we do by imitating and accelerating natural processes, and in result, provide a permanent and safe storage solution. Now, for our technology to work, we need to meet 3 requirements. So favorable rock formations, which are we prefer basalt. Then we need water, and a lot of water, and then a source of carbon dioxide. Now, this is what happens in 2 years. So the process of turning captured CO2 into stone underground takes less than 2 years, and this has been verified by monitoring methods. So this is sort of a before and after photo, because our method, we are filling all those pores that you can see here on your left-hand side, the before rock. You're filling them with those minerals, which you can see the pores have filled up on the after rock sample. So this is basically what we are doing. Now, as I said, we prefer young basalt. However, the storage potential in the world, if you only look at basaltic formations, are greater than emissions from burning all fossil fuels on Earth. So the storage potential is huge. And you can see Alaska there. You have some basalt for us, so we might potentially be able to come and do some experiments with you. So now, as I told you in the beginning, we are quite a little company, and we are a very young one. We are roughly 30 employees at the moment. But the project started in 2006 and was formally founded in 2007 by our founding partners, so Reykjavik Energy, the University of Iceland, CNRS in Toulouse, and the Earth Institute of Columbia University. But in only 7 years, Carfix was transformed from an idea on paper to a fully operational, cost-effective, and environmentally friendly industrial process to capture CO2 and H2S from emission sources, and then permanently store it in rock. So that happened in 2014 when we got the rapid mineral storage confirmed. Then in 2019, the Carfix company was created and then formally started on the 1st of January 2020. So we are very, very new and very, very, little, but growing a lot. So our mission for the future here is to become a key instrument in tackling the climate crisis by reaching 1 billion tons of permanently stored CO2 in as rapid as possible. But now I would like to remind you of these 115 gigatons that I talked about earlier. So that's only one of those 115. So there's a lot more to do. But why mineral storage? Why are we doing things a bit differently? The Carfix technology is thoroughly tested and proven by science and has been demonstrated to be considerably advantages over the more conventional way of storing CO2. So I've been talking a lot about our mineralization method, and then we have this conventional way that I haven't really explained. So the conventional way is to use older oil and gas reservoirs to fill them up with CO2 instead of oil and gas. But that's the conventional way. This is not our way. We are not linked with oil and gas, and we do not work with the oil and gas types of formation. So we use basalt. As I showed earlier, we are filling up those tiny little pores. So because of this, the Carfix technology is highly competitive because it is permanent and 100% safe, and even more cost effective than alternative technologies, and scalable, which I will come at later in this presentation. Why can we say that we have lower cost? That is explained because we are on onshore operations. We have a lot shallower wells, cheaper wellhead equipment, and lower operational pressure than the conventional CCS storage. This is Carfix in action. This is our operations in Hellisheiði and our testing equipment in Helguvík. This is all in the southern peninsula in Iceland. Yeah, so this is what we do. So scaling up this technology, we have 3 different scenarios that we are looking at on a parallel scale. So the first being the on-site capture and mineral storage. The second one, or B, the transport hubs with mineral storage. And then C, Carfix and direct air capture. So starting with A, the on-site capture and mineral storage, we have been doing exactly that at our flagship operations in Hellisheiði, which Gwen mentioned here earlier, where we have, for now, injected approximately 90,000 tons of CO2 since 2014. However, we are currently in an EU Innovation Fund project called Silverstone, where we are making Hellisheiði carbon neutral. So storing almost all CO2 and H2S from that geothermal power plant. Next, the transport and storage hubs. So this is Carfix by far largest current project under development. This is called the Coda Terminal Hub. And this will also be the world's largest mineralization sequestration facility. So what we are doing here, we are taking CO2 that is captured in Northern Europe by the hard-to-abate industry, liquefying it and transporting it to Iceland on these specially designed vessels. First phase will be operational in 2026, when we will have 500,000 kilotons per year, and then gradually reaching 3 million tons by 2031, or as you can see here. So we are currently doing environmental impact assessment for this. So yeah, starting constructions next year. But we have already drilled 1 well for this operational phase. So, and then C, last but not least, the direct air capture and storage, which I saw in the poll that people are quite interested in. The first example of the DAC technology combined with the Carfix technology became operational in Iceland in 2017 with the company Climeworks, developed this technology of removing CO2 directly from the atmosphere. The first one, named the Fox, the Arctic Fox, took 50 tons a year from the atmosphere. But now they have scaled that operations up to this 4,000 ton CO2 a year capacity, which is called Orca. And this is not their endpoint with us. This is already in operation. They are going to tenfold that with their newest project called Mammoth, which is under development in Iceland. So they are doing a lot with us, and all of their captured CO2 will be injected into the subsurface, or is being injected into the subsurface next to Hellisheiði geothermal power plant. But we didn't really stop there. There are so many possibilities in the DAC industry, so we wanted to help people as well, or help the companies develop their technology, because we need them as well, because we as a company, Carfix, we will not fix the climate crisis by ourselves. We need all hands on deck, and we would like to help in that innovation. So we are creating this DAC Innovation Park, where we have a lot of land organized for DAC deployment next to the Hellisheiði geothermal power plant, where they have access to renewable energy, heat, and water. And I don't know if you knew about this, but we did receive 2 X Prize grant from Elon Musk last year, I think, to develop 2 of these projects with Heirloom and Verdox. So this is ongoing project. But we don't want to stop there, because there's one thing in the industry that we're in about scaling up. We want to become bigger. We want to make more, do more. However, we also need to remember our R&D background, because if we stop our R&D, we stop developing and we stop growing as well. So we are always looking at opportunities of making our technology better. And then we get into the Seastone project, because the Carfix technology uses a lot of water when we inject into the subsurface. And for now, we have only been using fresh water, because we have a lot of fresh water in Iceland. However, that is not the case everywhere in the world. So by looking at if we can use seawater or salted water instead of fresh water, will open up a lot of opportunities for growing in areas that are not abundant with fresh water. So that's our Seastone project. I can't really do a Carfix presentation without mentioning the valuable support we have had from granting authorities in the EU. Iceland is not a part of the EU, however, we are a part of this funding scheme. So we have been so lucky to have been able to have grants from them. I have touched a little bit on the 2 last one, called Project Silverstone and Coda Terminal. I just can't really tell you how important this is. And if there are anyone out there that have the possibilities of funding small projects for the future, do it. I mean, this can only be good things that come out from this, like with us. Talking about that Coda Terminal, so that we got a 115 million euros for that project from the EU Innovation Fund. This is, I think, roughly $125 million, 130, something like that. So extremely, lucky with that. On that note, I would like to end this presentation by just telling you, being a really small company in an industry that is really new, unpredictable, it's so important to have the dedication of the team members, and that is certainly not lacking with us. I would like to show you a video of my coworker, which was located in a family vacation in Denmark when we found out that we got this Coda Terminal grant of $120-ish million. So thank you.
Getið þið sagt hvað er að gerast? Fenguðu fucking innovation? Innilega til hamingju, þið snillingar. Oh my god. Oh. Oh. Oh.
Yes, this is what it is, Carpix. Thank you. I assume the questions will be after Deirdre's presentation?
Let's just feel that. Well, yeah, maybe we should just go ahead and okay, we'll do that. We'll just jump right into Deirdre's presentation, and then we'll do Q&A at the end. And we do have a few that are already in the chat, so you could take a look at those too, Ragna.
Okay.
That was really fun. That was super fun. So I want to welcome our second speaker, Deirdre Clark, who is with ESOR, Iceland's Geosurvey, and so I had the chance to be co-located with ESOR and Okurstofnung when I was an Arctic Fulbright scholar. I think ESOR is the largest geothermal geotechnical company anywhere in the world, if I'm correct. So I'm going to go ahead and turn it right over to you, Deirdre. Deirdre, thank you for joining us.
Yeah, thank you. It's a pleasure to be here. My name's Deirdre Clark. I'm a geochemist at the Iceland Geosurvey. Actually, I was originally born in America, in New Jersey, so it's nice to speak to some fellow countrymen, though in Alaska, and I have not had the pleasure of visiting Alaska yet, but I hope one day. And so I will speak more from a geothermal perspective, how ESOR has been entering in CCS here in Iceland in close collaboration with Carpix, basically with whatever they need, we're always willing to assist. And first, a little bit about ESOR. So in English, we call ourselves the Iceland Geosurvey, but in the Icelandic name, it actually means the Icelandic Energy Research Institute. So it's not exactly a USGS. We are owned by the Icelandic government. We do provide specialized services to the power industry here and the government, as well as international companies. So we operate on the free market on a competitive basis. And any profit that we do get goes back into scientific research and to further strengthen ESOR. We've had over 75 years of experience. The organization and the names have changed over the years, but basically since 1945, there's been a lot of involvement in the development here in geothermal as well as abroad. And since 2003, ESOR has been as it's currently standing now. So just a little bit of a background on geothermal utilization in Iceland, because it will help also to understand why Iceland was not so afraid of actually diving into the world of CCS. So in Iceland, we are fortunate enough to have quite a lot of renewable energy sources. So 70% of the energy does come from geothermal, and then about 20% from hydropower. And over time, we've actually been able to increase our reliance more on hydropower and geothermal in comparison to oil and coal, to the point that we're actually not really using coal anymore. And then wind energy is just about to come online. There's a kind of a strong wind here, so I think there is quite a lot of testing being done on that. Let's see. So if we look at a map of Iceland, think of Iceland as a cold Hawaii that's also on the mid-oceanic ridge. And so actually Iceland's being pulled apart about 2 centimeters a year, and you have quite a volcanically and seismically active rift zone in the center of the country, which is the same location as our high temperature geothermal areas. And so when I'm speaking high temperature, I'm speaking about 200 degrees Celsius and above. We have plenty of lower temperature areas, next to and outside the rift zone. These high temperature areas we've been able to further develop into different geothermal power stations in Iceland. We have about 7 flash power stations, and the capital area, Reykjavik, is here. That's where, I'm in Reykjavik. I guess, Ragna, you're just on the other side in Selfoss. But anyway, and Carpix, actually, the pilot project was connected with the Headless 80 power plant, which is just here, just outside of Reykjavik. And the Iceland Geosurvey has been a key actor in the development of all of these, and the first one was commissioned in 1969 and is actually still ongoing. just to speak about like geothermal, the fact that yes, we have a lot of power from there, but that's about 40% of our usage of geothermal goes to power generation. The rest goes to quite a bit to space heating. Thankfully, we have nice heat. And also we have for swimming pools, wonderful places to be. And there's snow melting, also for snow melting industry, fish farming, and greenhouses. So in the exploration of all these geothermal areas in Iceland, we have been applying many different types of geoscientific methods, as well as drilling different wells. And this also goes for when we're exploring and developing other areas throughout the world. And so we always do this in a stepwise approach, and everything has to be tailor-made to each site because you know, you don't have the same geology everywhere. You don't have the same infrastructure everywhere. And so in our exploration phase, like we have different steps within there. So we're reviewing whatever data we have. We're looking at what geothermal is there, conducting any geochemical studies, doing some geological mapping, geophysical exploration, drilling any potential wells to gather more information about what we're working with, and then coming up with an idea of like, well, how can we use this resource and continue? And so once we go through this exploration and have an idea of what we can do, then you're drilling even more wells for production and testing, conducting different environmental impact assessments, coming up with the design of the power plant, getting the different licenses, making sure you have all your investments. And then this further goes into making your detailed design, actually constructing your power plant, drilling more wells. And so this is actually a picture of Headless Haiti when it was under construction. And then you're testing out everything, commissioning the power plant, training your personnel, and then operating. Power plants in Iceland typically, well, we'd say like a lifespan of 50 years. I mean, I guess most people say 30 years before they're written off. But again, we've had ones running since 1969. So how does this, like, how is it all connected to CCS or CCUS? Well, the thing is, a lot of the steps that we do in actually exploring and developing a geothermal resource, you can actually take that knowledge or those skill sets and apply it to carbon mineral storage sites, so to the development and the implementation of them. So when CarbFix, the idea was first being brought about, like I should say, I was a PhD student among this. I also got an EU grant. Thank you. It was very nice. And so I've been involved with CarbFix since 2014. So when we were trying to first like think of the idea, well, the group of people before me, Headless Haiti actually offered up, you know, an area next to them. And so they were, because some wells had been already drilled there, they were able to say, hey, there's part of the geothermal field we're not really using. So why not test the method here and go for that? So a lot of the personnel like originally involved, they had all geothermal experience. And so then over time we realized, oh, actually, like, this is quite useful to know, like, all the reservoir modeling that you do for a geothermal power plant, well, you can take those skill sets and also do it for looking at your carbon storage reservoir and so on. The sampling you do of fluids, well, we can do the same thing. We're sampling wells and so on. So just to explain a little bit how ESOR has been involved and like kind of the different tasks I'm talking about are very similar to what we're doing already for geothermal. So we offer drilling consulting. So we've been helping with well siting and design, drilling supervision, logging of the wells and testing of the wells, and any on-site geological consulting. We've been helping to characterize solids and fluids. So particularly, we often get samples that we can analyze for whether it is geothermal water, gas, and steam. So if it's coming from Headless Haiti or Nesavitlir, though actually, I think that's more Reykjavik Energy doing that at the moment, or analyzing groundwater and seawater, like especially with the Sea Stone project and Coda terminal. Sometimes we're getting samples from these wells. And then, with each of the wells that are being drilled, you might have some cuttings, not so common cores, but at least the cuttings, which we then can analyze and draw up reports and get more information about the geology. And then you do some tracer tests. So in a geothermal reservoir, you put in a tracer in order to have an idea, okay, how fast is the water moving from A to B? And this gives you a better idea of the hydrology of the area. So you would maybe do the same thing also in a carbon storage reservoir. And so with that, we can help assess the reservoir. So help build a conceptual model, use these tracer test injections and help interpret them with regards to the model. Include also geophysical measurements, so also TEM, resistivity, help to estimate like the potential of how much carbon could be stored, evaluate the gas injection either prior and also during the injection, and then always improve our reservoir modeling for this. And then Rachna briefly mentioned they're working on the environmental impact assessment for Coda Terminal. This is a big step. This is the same also for geothermal development. It takes a lot of time for this, and but it is a good backbone. So you're doing different surveys, geophysical and the seismic surveys. You're also trying to create a background to like how much CO2 is already naturally there, which is a little bit difficult versus making sure you're not releasing any CO2. That's also often a question everybody asks. And then conducting any environmental monitoring, coming up with a plan for this, and modeling the groundwater to try and make sure that you're having the minimal impact on the environment around you, particularly if you have a residential area nearby. And this is something we already do for geothermal power plants. Just to kind of conclude, these are the different services we've been offering, particularly with regards to geothermal, but many of these we're hoping to be able to also offer for various people who are interested in CCS, particularly the mineral storage side of things. And we have been involved in most geothermal projects in Iceland, and then have been involved in geothermal development all over the world, particularly these days in Latin America, Africa, and Asia. And so if you have any questions that you come up with later, here's my contact information. And I guess we just open the floor for questions. So it's much better to have a nicer discussion.
Yeah, thank you so much. And we have about 15 minutes or so for questions, and there's been a few that have been put in the chat for both of you. I will say, like, ESOR has been a really fantastic organization on the training side of things too. You've worked a lot with the geothermal training program, obviously in Iceland, and have worked a lot with folks from around the Arctic, around this Arctic Remote Energy Network Academy, which is a partnership with Iceland, and ESOR has been really involved in that. So thank you. We thank ESOR for being a good partner in that. So just a few kind of questions. I think that these might be, Ragnar, maybe for you. There's a question about how far the carbon is transported from the point of origin to the point of storage. So is that like happening right there, or are you actually moving it in a pipeline to the point of storage?
So that depends on what type of project we are working with. So if it's a point source, so the A in my presentation, we are not, under a kilometer. We are, that's the idea behind point source, that we get the source of CO2 and the injection at the same location. Same with the DAC companies that we have been working with. These can also be considered as point source. However, for the Coda Terminal, we are getting CO2 from the hard-to-abate industry in Northern Europe. So then we are using ships, or especially the designed vessels, to bring that CO2 to Iceland. But the injection wells are very close to the harbor where we will get the CO2 ships. If that answers the question.
Yeah. No, thank you. And then in terms of how long do wells, how long, what's the lifetime of a well, and how often do you have to drill new wells? Do you plug those wells? What's the life cycle of the actual injection wells?
So we have been injecting in 2 wells in Hellisheiði almost since the beginning of the project, and in how do you say this? People always think that we are clogging them. We are actually making the wells better.
The injectivity has improved.
Yes. So because the CO2 is a bit acidic, we are actually making those rocks better for injection.
Okay.
So we are not clogging anything.
Yeah. So one of the questions here is, do you inject supercritical CO2 into shallow basalt wells, or that's just
no? So we are mixing CO2 with the water. So it's not supercritical CO2 as in the conventional CO2 storage or CCS. We are mixing it with water and injection it together, basically. It's a little bit like a soda stream machine, a big soda stream machine that we're using to mix CO2 and water together.
And how do you know that what you're actually injecting into those wells is going to remain underground? Like, is there some sort of like a maximum per well, some kind of a rate at which you're injecting the CO2 and the water and the fluid? How do you monitor that?
So how do we monitor the CO2? Can you be more specific?
Just knowing that it actually turns into stone, that it stays underground, and that you're not seeing some of that, kind of seep back out. How you monitor that?
Yeah, so we have these monitoring wells where we are measuring how much of the CO2 is coming out of those wells. Maybe Deirdre can comment on this. This is her PhD almost.
Yes. I was lucky enough to join the project when it was still a project, not a company, when they had just started the injection at Hellisheiði and were injecting in the one well and started some injection into a second well. And so because you're at a geothermal reservoir, it's also a perfect testing site because they already had wells in place and they had some production wells that they're already using. So we were able to also go and sample the geothermal fluids, and then I could do some geochemical calculations to try and compare, like, well, what would I expect to see if actually no CO2 was stored? Tracer tests were also done later on to look into this, but it is very expensive to go and get a core. Of course, we would love for that, but it's a big reservoir and it's a lot of water going through.
And the idea is that the CO2 rich water is actually heavier than the surrounding geothermal water, so it's actually sinking. So it's quite hard to get to those rocks because they're transforming quite deep into rocks.
So I guess the chemistry has been really the strong point in terms of the monitoring, looking at the fluids and then putting all the information about the reservoir into your model and to try and model it and to get a better idea where is everything going. So lots of reservoir modeling, lots of geochemistry and calculations.
All right. Well, I'll just stick with the technical questions for a minute, and then we'll switch over to economics. But quickly, Deirdre, what sort of modeling are you using when you're modeling those wells? And then I've got a couple other questions along those lines.
Well, so Carpfix and ESOR have been using Leapfrog and Tough React. So in the geological modeling and things, and then Tough React trying to incorporate the chemistry side of things. It takes a little time to develop this. And then, of course, Tough and Tough React are not the easiest programs to run. In terms of some geochemical calculations, we've been using a lot of Frixie. So, USGS, open source, pretty simple, and you can do some 1D there. But yeah, it's a lot to do the 3D and continue to work on. But this is something that's been building over the years since, even the CEO, Edda Sif Aradatir of Carpfix, she did her PhD and was working on the first sets of models for the pilot project back in 2010, 2012. And so much has happened since then.
So a couple of questions. Jessica Larson is interested in what temperature the water is that you're using. And then Don Reamer is interested, like, do the wells sort of block themselves with precipitate, and would horizontal drilling provide greater contact with the formation? So a couple of questions on.
I'm actually not quite sure what the temperature of the water is. Do you know that, Deirdre?
Well, I guess it depends. If we're talking about headless Haiti, then we're talking 250 degrees Celsius, which is kind of the upper limit to carbon storage. But I guess in the expansions that you guys are working on, aren't you looking at lower temperatures, more like 50 degrees, which is more ideal
Yeah, I think so.
carbon storage? So we've been looking at like the upper boundary. It's like, okay, we don't want to be more than 250, 270. Much prefer carbon likes to be, I guess you have faster mineralization rates, so it's faster for the gas to turn to stone at lower temperatures.
Yeah. And for the horizontal drilling, so this is the misconception between the normal CCS versus our CCS. So because we are not targeting a specific reservoir area that, like a balloon, like in the regular CCS, we are targeting just tiny little holes inside the rock. So horizontal or vertical or diagonal, it doesn't really matter. It's more of getting the right pressure, the right temperature, and etc.
Right. We'll switch over to a couple of questions on the economics. So one of them is just a pretty straightforward question. Do you know what the dollars per ton of storage that's expected for the Mammoth project?
Oh, for the storage part of the Mammoth project, it's about $25 per ton, but that's the storage part. I don't know about the capturing part of it.
Okay, and then I'll just kind of look at this. Would it be reliable to have CCUS plants in every large scale industry? So I assume this is sort of point source capture by considering LCA of the products and their emissions. Like, what are your insights about the CapEx to achieve this is like a more sustainable practice and more locations? Do you guys have any thoughts about the economics?
So what we are really counting on is that the price of CO2 emitted goes up in the future, so that the price of emitted CO2 is larger than the price of actually going into the trouble of storing it or using it in some way. So we are seeing the rise of ETS prices in the world. So that is what needs to happen for these kind of projects to be a good investment.
So I'll add a question of my own here too. I'm curious, like with the Climeworks direct air capture, would that work in a colder climate? I mean, Iceland is cold, but not as cold as Alaska is. And would you have some challenges there regarding like sub-freezing temperatures?
Now, I can't really talk for climbers, but I do think that it is okay. I mean, for their first operational unit, the Arctic Fox, they had a lot of troubles because the location of Headless City is, it's on the top of a mountain. The harsh weather there is it's crazy. And the learning curve for them was exponential because of the difficulties of the climate here. However, I don't know if they have like tried it in minus 30, 40 degrees Celsius. I don't know, but at least they do learn a lot by having that little unit.
You have to deal sometimes with hurricane force winds here, and a lot of precipitation and ice. So at least like they had a lot of experience with like constant freeze thaw and lots and lots of wind. Sure, that was a headache, but it's really good way to test the equipment. And that was the idea when they first came. They're like, well, we want a harsh climate and you guys got one. So here we go.
Yeah. And they got a harsh climate for their unit. That poor thing.
Yeah. Yeah, I definitely agree that Iceland can be a pretty variable and tough climate for sure. So, I'm always intrigued at how Iceland does such a nice job of working together between sort of the public sector. I often think of ESOR as being kind of like the Alaska Center for Energy and Power in some ways, and then supporting, private sector companies. And so I'm curious, like just kind of from a strategy standpoint, how you guys kind of think about that, because you've really built up a really nice ecosystem with a lot of small companies that are doing some really innovative things across a number of different kind of sectors. And I'm just curious, like if you have any thoughts on that, because I think it's something that Alaska could really learn from as well.
Yeah.
You can okay. I mean, I can start. It's fine. Actually, this is something that I've really come to appreciate when I was doing my PhD here, was the fact that the hierarchy there wasn't such a hierarchy, and you really could get in the room like policymakers, scientists, businessmen, like all in the same room discussing things. So that really helps. And also just the openness of everything. Like the CarbFix idea, when it came about, I mean, it was partly like you had some scientists thinking like, hey, like, what can we do? You had the previous president of Iceland, Ólafur Grimsson. He was kind of interested. I mean, Al Gore had come to give a talk, and then you had Reykjavik Energy, who was just like, hey, yeah, why not? Like, we're looking for different ideas, and they have a really strong R&D department. And so you just, I don't know, like it doesn't make sense to close the doors and keep everything a secret. Like, I mean, I understand there's patents and some like maybe business ideas to keep secret, but in general, like to try and share knowledge and open it will only be benefit to everybody. And you never know where an idea comes from. And how something grows. So, I mean, CarbFix would not have been successful without the openness of people and without the inclusion from students to business ideas to politicians to everything. At least that was from my perspective. And I think ESOR they also like things to be open. And, that's why we work so much with training and educating many young people around the world, working with different companies, because again, you're sharing knowledge and you don't know where it ends up, and you don't know where the next idea comes from.
Yeah, I mean, exactly. We at CarbFix has always been very open about that. We are one part of the solution. There are going to be hopefully hundreds of more, because the amount that we need to do in order to solve this climate crisis is more than just one company is able to do. So just being open, talk about our technology and our road and how the difficulties we have faced, just for others to learn from it and hopefully move the technology further. It's just so important.
Yeah. Well, thanks to both of you for sharing a little bit about what you're doing in Iceland. I really appreciate the time that you've taken in your evening to be with us today, and I hope that we can sort of keep this conversation going. I think there's a lot of similarities between Alaska and Iceland, and I hope to meet both of you in person at some point in time in the near future. So thank you.
Thank you.
Yeah, thank you as well.
So I guess with that, we'll just transition right into our next presentation. We're pretty much right on time, which is amazing. But it's really my pleasure to go to another part of the world that I also view as having some similarities to Alaska, and that's the province of Saskatchewan. It's my pleasure to introduce Ran, who is the President and Chief Executive Officer at the Petroleum Technology Research Center. I view Ran as kind of one of those people that's a single name sort of person, So Ran, I've known you across a couple of different careers that maybe you've had. Met you first when you were at Sask Power. Really enjoyed some of the conversations we had about how we produce and use energy, both in our cities, for our industry, and for our remote communities. communities. And so I'm really appreciate the time that you've taken to join us here today. And I think you're actually going to be coming in person to the Alaska Sustainable Energy Conference as well. So I'll go ahead and turn it right over to you.
Thank you so much, Gwen, for a warm introduction. The one thing I like really working with folks like you in Alaska and utilities is the warm welcome and the openness and transparency to collaboration. I really, really appreciate it. I'm from Saskatchewan. I feel whenever I come to Alaska, I feel like home. And you guys show such a great hospitality. And thank you so much for that. I really appreciate that. And once again, thanks for the invite. I'm going to talk about the carbon capture, utilization, and storage and some of our experiences in Saskatchewan. And I want to acknowledge I'm in beautiful Treaty 4 territory, homeland of Métis and Regina. That's our head office here. And PTRC has been in business for the last 25 years. And predominantly, our work focuses on carbon capture, utilization, and storage. The utilization is the enhanced oil recovery. I have a quick agenda. I want to spend more time answering questions. And, I just have a quick agenda about PTRC and the most important thing about SAS power plant. That's the first carbon capture plant ever built in the world, post-combustion. And what are the advantages we have in Saskatchewan? And also, there is a really good tax incentives happening in states and Canada. And also, we're hosting a Williston Basin conference. Let's jump into the PTRC introduction. I said, we've been in business for 25 years. We were founded by Canadian government and the Saskatchewan government in 1998 to maximize the research and the field expertise to develop solutions for oil and gas industry. So we focus heavily on a lot of net zero activities of 2050 net zero. And also we have done a lot of work on carbon reduction. I will show you some really cool pictures and some of the work. And we are really good in making the CCUS commercialized. Because I want to say the CCUS is not a coffee table conversation when compared to wind and solar. Because CCUS is still a myth, still new, but it's a workable solution. I think definitely CCUS will play a very important role. If you look at reducing the greenhouse gas emissions, we need CCUS because it will be a very important part of the toolbox to reduce the carbon intensity and carbon emissions. Because I want to touch base with the SAS Power Boundary Dam plant here. This is the first carbon capture storage plant post-combustion built in Saskatchewan. And we are very proud about this in Saskatchewan because we almost captured, you can see, 5.2 million tons of CO2. That's a significant amount of CO2 is captured from that power plant. And almost it produces 115 megawatts of power to power 100,000 Saskatchewan homes. The most important thing when it comes to carbon capture is you need to find a utilization and storage because capturing carbon is not a problem. There is a lot of cool technologies now to capture carbon, mostly like a CANSOLV and Mitsubishi, like amine solutions. But we have to find a way to utilize and store it. In Saskatchewan, we use CO2 for enhanced oil recovery. You can see in the 3D picture here in Weyburn, where we are injecting CO2 in a closed loop system to produce oil. I think people say, yeah, you're using carbon to produce oil, but I think that's a really good environmental way to produce oil by using CO2 because you're capturing the CO2 and injecting in the ground and producing oil. So in Saskatchewan, almost 40 million tons of CO2 is injected for enhanced oil recovery. That's a pretty significant number. There is another picture called on the right, Aquistore, which is a deep saline storage formation where we are storing CO2 there, almost 3.4 kilometers deep. I trust Alaska might have a similar geological formation for CO2 storage too. In Saskatchewan and in Alberta, we are really blessed with a really good geological formation. So we are able to inject CO2. Every day we inject 300 to 400 tons and the maximum we have injected 2,600 tons of CO2. So this is a real time and it's a live experience. So that's the advantage we have in Saskatchewan is know-how. So basically, we have done it. And the most important part being the first in a capture plant and storage, you're going to learn a lot, good, bad, and ugly, because it's great, but also the lessons you are learning by being the first is very, very important. The information we are able to share and the information we are able to transfer to other projects and the industry nationally and internationally is very important, because we have a data for last 8 years of injection, because that's what the industry is in need, especially a lot of new projects are coming on board. So the amount of information we have is really, really important. And again, you can see that picture there showing that what 500,000 tons of CO2 storage does, taking 125,000 cars off the road per year. So that's a pretty significant, because if you look at it in terms of the population of Saskatchewan and the amount of CO2 we captured is pretty significant number. Again, the most important thing for regulators is measurement, monitoring, and verification. Because as being a research project at the AccuStore, we are able to test 30 monitoring technologies. That's very important, because industry really needs to understand what is the best monitoring measurement technologies needed for storing CO2. And you can also see that CO2 plume monitoring from 36,000 tons to 272,000 tons, because we have a model we do and we monitor the CO2, how the plume is moving, because that's a very important for regulators to know where the CO2 is going to be. People ask me the question, what will happen to CO2 in next 50 to 100 years? I'm already in the low 40s. I don't know how we'll live for another 100 years to answer the question. But we need to have a mechanism to show that CO2 is stored safely and able to measure and monitor. And also PTRC, we are very well experienced in developing those international standards for CCUS, because right now one of my senior engineers is a Canadian co-chair for ISO standards TC265. And there is 24 to 25 countries involved in developing that national standards, because it's very important to have a standards for industry to develop CCUS. And we have a very hands-on experience. And also we are hosting an event in Regina on June 5th to 9th. The international ISO panel members are coming to do more work. And we are also making using this opportunity to educate the people about CCUS standards, that PTRC is a part of Saskatchewan. And this is the main thing, why CCUS is getting so popular, because of the tax incentives. I think in US, the 45Q, most of you know it really well, lower 48 and stuff. There's a lot of projects happening. You can see that number of dollars available for CO2 storage and UR, that's pretty significant. And compared to Canada, we have a small carrots. We do have some tax investments available for investing in a CCUS project. I think you can see the bottom of my presentation. They're expecting CCUS economy going to be a $4 trillion economy by 2050. I don't have a crystal ball, but like I said earlier in my presentation, is CCS will play a very, very important tool in a toolbox to reduce the climate change and also reducing the carbon emissions, because we have a projects proven already, but it's not, moving fast enough. But with this tax incentives, I'm seeing a lot of movement and a lot of opportunities to work together and make CCUS as a commodity. Because if you make CCUS as a commodity and learn from people like us and experience what we have, we can deploy CCUS faster. And another conference we are hosting in May in Saskatchewan. It's a Saskatchewan CCUS Summit. It's May 2 and 3. I think we jointly host with North Dakota Petroleum Council. It happens 1 year in Bismarck and 1 year in Regina. It's kind of like alternates every year. This is the 30th anniversary of the conference. And we are very proud to partner with the state of North Dakota on this conference for the last 30 years. So it's a great partnership. And this is the companies we work with. And you can see we work with the ERC and a lot of organizations which have a big presence in the states in USA, and also international organizations like Japan, JOGMEC, and also we have done work in Australia. So you work with pretty much everything. And we are looking forward to collaborating with Gwen and the University of Fairbanks too. So we would like to have that more collaboration and see how we can help and collaborate together and help with the CCUS deployments in Alaska. I want to say Alaska has really very vibrant, sustainable policies and the opportunities. And we are looking forward to work with you and happy to answer questions.
Thank you, Ran. And I know that you wanted to kind of keep it open for Q&A. And so Frank actually has a question here about about CCUS at the Boundary Dam power generation plant there. Does it increase the cost of electricity for the customers?
No, that's a great question. But when we built it that time, there was no carbon tax. But right now in Canada, there is a $75 a ton for carbon tax. Like every ton of CO2, when you produce, you are paying a carbon tax from the emissions from the coal plant or a natural gas plant. By 2030, Canadian government wants to shut all the coal plants, or if you have to have a carbon capture. Like you have to reduce the carbon. Otherwise, you're paying millions and millions of dollars of like a carbon tax. So in terms of that, having a carbon capture plant, so the price is not going to make a big difference. But again, there is a initial capital investment is pretty high. That's true. But compared to what we built 10 years ago and today, the cost come down significantly. Because I want to say kudos to the industry and the research and development of CCUS from all the universities and the institutions and organizations. They really reduce the cost of building a carbon capture plant now. And I showed you that couple of tax incentives, right? Like in the US, they're giving $85 a ton for CO2 storage and $65 for enhanced oil recovery. That's pretty significant. So you need some carrots to make this work. But there is an opportunity now because there is a carbon tax attached to that in Canada. So you better reduce it. Otherwise, you're paying millions of dollars in carbon tax. That's not going to help the price of the power. It will go up, right? So having a carbon capture a plant attached to a cement or steel or a power, it will make a big difference in terms of carbon tax. And also you're getting a tax incentives from the Canadian government right now.
So what are the biggest barriers to sort of expanding this to other like direct point source capture projects? Like what's the limitation in Canada in particular?
I think in Canada, it's really good. Right now, there is cement factories. If you look at the commodities, right, cement, steel, refineries, they all produce a significant CO2 emissions. So right now, there's a cement plant in Edmonton. They're putting a million tons of a capture facility right now. They're working on it. And we are also working with the storage company right now in Edmonton on a risk assessment of capturing carbon is really easy right now from any set sources because of the technology development. But the most important part we need to think about is utilization and storage. Because utilization that I know of can be used as an enhanced oil recovery, EOR, but the other one is the permanent storage. So like I said, we have a really good geological formation to store CO2 in Alberta and Saskatchewan. So that really helps a lot in deploying the CCUS faster because we're able to utilize for oil production and also you have an advantage of storage. So we are fortunate to have that. And recently we did a study for Vietnam for Asian Development Bank, just looking at the roadmap for Vietnam as a country to how to avoid the barriers and how to develop CCUS. because the biggest concern is the storage. The capture facility, you can, but again, the utilization and storage is the two important part we have to keep in mind, because capture is complex too, but it's not a rocket science. You can do it because there's a lot of plants already working with capture facility, and we have a decade of experience in Saskatchewan making it commercialized. So in terms of a barrier right now is lack of awareness. Like, it's not a coffee table conversation. When you talk about wind and solar and geothermal, people know right away. But when you say CCUS, people take 10 seconds or 20 seconds pass to ask what it is, right? It's not a commodity yet, but it's coming up because people are understanding. Even COP27, COP28, there's a lot of focus on CCUS because, like I said, it's an important part of a toolbox to reduce the carbon emissions.
Yeah, thanks, Rand. And just so, could you also just kind of clarify again, what proportion or what percentage of carbon is actually captured and sequestered compared to what the plant is producing? And are there downtime, like how much downtime does the CCS component have at the plant? Does that make sense?
No, that's a great question, Gwen. Like, when the plant was started operating, it's a public information. We had some issues because it's the first plant. Imagine a power utility built a chemical plant, right? But that's where you learn from it, right? The amine concentration and stuff. But at present, it's able to capture almost 85% of the CO2 coming out of that number 3 facility, Boundary Dam 3 facility, because there is a SO2, right? Because when you look at the capture facility, it takes the SO2 separate and also the CO2 separate, right? So in terms of CO2, it's able to capture 80% now. Out of 80%, almost 70% goes for enhanced oil recovery. You get paid to sell the CO2. The remaining comes to the site that we manage called AccuStore, where we are injecting permanently 300 to 400 tons a day. So there is 2 uses of the capture, right? One is for enhanced oil recovery. One is for storage, but you can do permanent storage too. You don't need to do EOR. If you don't have a proper EOR facilities and sites in your province or state, but there is a permanent storage. Again, there is a tax incentives right now. So people don't mind storing CO2 permanently because there is quite a bit of money available from the 45Q in states, and even Canada is giving 50 to 60% tax incentives. So you capture almost 90% of the CO2 because it's not 100, but the downtime, you have to always do the maintenance, right? When you look at the plants, so it's always going to be there, but you have to keep that in mind. But it's getting better because the technology improved a lot. So it's more efficient than 8 years back. It's kind of like how the electric cars and hybrid cars are in roads right now. Even our cars compared to 10 years, better fuel efficient. So it's better efficient, right?
So just to kind of clarify, so the CO2 that's used for enhanced oil recovery, and you're saying that's a pretty large portion of the of stream, does that stay underground? Does that stay sequestered underground, or does that get reproduced?
I think most of them stays underground, but it's a closed loop system. You when the oil comes out using CO2, there's a CO2 will come out too. Then there is an extraction system. They separate the CO2. They keep injecting again. Because with the CO2 injection, the amount of oil production goes up 25%, especially in depleted wells. So you are not going and drilling a new well. So you're using the existing wells and you're improving the production. It's called a CO2 EOR flooding, right? CO2 flooding. So you're injecting CO2 to produce more oil and economical too. 1 ton of CO2 almost produces 3 barrels of oil. So that's a pretty significant when you compare to the oil price right now. And also you are not going and conventionally drilling more wells, right? So you are protecting the environment too. But still, the need for oil is not going to go down. Even I just saw the news last month where in states, the president approved a big project in Alaska, 180,000 barrels of oil, because it clearly shows that we are still dependent on oil and gas for a few decades. You cannot just shut off. You know what I'm saying? But producing oil using CO2 is not a bad thing. It's a good, because we are still capturing and storing it, right?
So, Alaska actually has a huge amount of coal resources, right? And so I'm kind of curious about your perspective on the idea of, combining point source capture with coal generation. I think one of the biggest concerns about coal plants is the emissions associated with those. But the idea of capturing that CO2 and then sequestering that geologically, permanently, or utilizing it in other ways, that seems like it would be an appealing way to the word clean coal is a little bit of a dangerous word in Alaska because we've had some not great history with that all the time. But, nonetheless, that concept of cleaner coal, I'm just curious what your thoughts are in terms of the future of the coal industry related to the growing opportunities around CCS.
Actually, honestly speaking, the clean coal or coal, whatever. But main thing is right now, I want to say there is a technology available to abate the coal. It's not that you have to, even for gas. So there's a lot of natural gas plants, not only coal plants, right? We're talking about anything you're using fossil fuel, refineries, cement factories, and everything produces CO2. There is a technology available to capture it. So what we are doing in Saskatchewan is right now with PTRC is we are looking at the hub, storage hub. So looking at all the set point sources from refinery, from a gas plant, existing coal plant. And also we are looking at the mining, like potash mining here, because Saskatchewan is also very energy intense province, like Alaska. We are almost similar. So we are looking at that, taking all the set sources. And like I said, we are very fortunate to have a really good geological formation and also EOR, how we can utilize that. So you can bring everything into a hub model, like using the pipelines and capture everything, and you can put it in a one permanent location or few permanent locations for storage. I believe that your Alaskan Geological Society will have a really good data about your deep saline aquifer formation. Then based on that, you can do work, University of Fairbanks can do the work looking at how we can take the set point sources and combine and put those CO2 in permanent storage or EOR, or maybe there might be some utilization opportunities, which I don't know of, but I know that one utilization is EOR. That's what we are very familiar in Canada right now. So there is an opportunity to make it as a hub model, because instead of using one set and one point, if you combine everything together, that's more economical and cost effective. That's the work we are doing right now in Saskatchewan. We are looking at that all the set point sources to make how we can make it as a hub, like the CO2 storage hub. It's happening in Alberta too. There's two projects are happening very fast here. Yeah.
And so those projects, to what extent do they, obviously you've got the carbon tax, which is definitely a driver, but to what extent are these requiring government subsidies? To what extent is this going to be something that makes economic sense without any additional subsidies? Any thoughts on that?
I think that's clearly when I showed the slide, right? Even in States and in Canada, the both are giving a big subsidies, because I want to be, very direct is when it comes to CCUS, one of the issues is it's not a commodity, right? It's not like a price of the market. So you need incentives to start building those projects out. Without that, it's really hard, because if you look at the utilities and the cement factories or refineries and oil companies, because there's a significant capital investment needed, right? If you don't have some subsidies, that's what I put it in my presentation, carrots versus sticks. So fortunately, the Inflation Act in States, there's really good carrots. It's a good time to build. Even in Canada, there's $2.6 billion of tax incentives. So it is available right now. But if you look at 10 years back, we don't have it. But at present, there is enough incentives to make these projects feasible. The reason is you're getting significant amount of money for storing CO2, for EOR, and also for permanent storage, right? So I think that's the right way. I think the governments, we all complain about the governments no matter what, but I think they're also taking the initiative to enable the CCUS industry to move forward faster. Otherwise, they wouldn't give the significant incentives, right, to make it happen. Again, the problem is, we don't have hundreds of projects working to take the example and build faster, right? It takes time because if you look at refineries, there is hundreds of thousands of them to build one. It's not a cookie cutter when it comes to carbon capture, but that's the opportunities like this conversation and working with universities and research to develop these opportunities to build faster and make it feasible. And not only that, and also the safety, right? The measurement, monitoring, and verification for regulators to make it safe. That's the way we are going to move forward. But I know my answer is the incentives are there to make it happen right now.
Well, thank you. Thank you so much, Rand. I really appreciate that. I'm really glad that you're taking the time to come over to Alaska again. So thank you. I think that our mutual friend, Greg Peltzer, is also going to be coming over as a speaker for the Alaska Sustainable Energy Conference. So thank you. Appreciate your time. I know you're a couple hours behind us as well. And so have a great ahead of us. Sorry, I always get confused about that. So have a good afternoon, and thank you very much. We'll see you again soon. And
Okay, welcome back. Thanks everyone for your interest in CCUS and for participating in this workshop. And thanks to Gwen Holdman and this morning's presenters from Iceland and from Canada. It's really great to see carbon capture being successfully put into operation. Now it's my pleasure to introduce you to our next presenters, Chris Arms, Head of Americas Development at Storegga, and Ellie Lashko, CO2 storage geoscientist at Storegga. So Chris currently leads the Americas development team for Storegga and spent the first 15 years of his career working in industrial utilities and renewable power generation. Before switching to carbon capture and sequestration in 2020, he spent 17 years in upstream oil and gas in commercial and country management roles. Chris is a chartered engineer and member of the UK Energy Institute and received his master's in fuel and energy engineering from the University of Leeds in the UK. Ellie Lashko is a geologist by background, working on carbon storage projects at Storegga across the globe, including the UK, Norway, and Southeast Asia. She's been part of the delivery team for the Acorn project, one of the first carbon storage projects under development in the UK. Ellie holds a master's degree in petroleum geology. Thanks for joining us, and we look forward to your presentation. Chris, Elle?
Well, thanks again, Frank, for that introduction, and good morning, everyone. First of all, I'd like to start on behalf of Elle and I by thanking the organisers today for the invitation to speak. I've joined a number of the presentations over the last few days and have found them both of high quality and very interesting. So Elle and I have two objectives. One, to keep our presentation high quality, but more importantly, to keep you interested. So hopefully in the next 15 to 20 minutes, we'll be able to do that. Unfortunately, having said that, this is the one slide our legal team have asked me to add into the deck. So I'm going to leave that up on the screen for a few seconds before quickly moving on. Okay, in the next 15 to 20 minutes, as I said, I'm going to start by giving a brief history to Storegga, explain a bit about where we've come from and where we're going. I'll then talk about the Acorn project, which is the anchor project, if you like, of the business in the UK, how that's been developed. And then I'll hand over to Elle, who's going to talk a bit about how we've transferred the learnings from developing that project to new projects elsewhere, including, hopefully, Alaska. So Storegga has over sort of 15 years of background, starting originally as a company called CO2 Deep Store back in 2007, which was founded by a number of senior members of the oil and gas industry who had a desire to move more towards a sort of a carbon capture and storage future world. That changed or evolved into a company called Pale Blue Dot in 2013. And in the period 2013 to 2020, Pale Blue Dot developed the initial founding work that had been done by CO2 Deep Store on reservoirs and stores, picked up and developed the Acorn project based initially on a power station in northeast Scotland that was capturing CO2, but very quickly developed into the Acorn project. In 2020, Storegga picked up or acquired the Pale Blue Dot business and its people and resources, and has spent the last 2 years really accelerating the development of Acorn, as well as expanding the group's activities outside of the the UK into Europe, Asia Pacific, and the US, which I guess is in part is why Elle and I are here this morning to talk to you. Today, Storegga has project activities and offices in the UK, Norway, Singapore, and the US, based in Houston. And we have around 90 employees working globally on full chain CCS projects. So that gives you a little bit of a background of who Storegga is. Acorn, what is the Acorn project? Well, Acorn is a joint venture project between Storegga, Shell, Harbour Energy, who are now actually the largest producing oil and gas company in the North Sea, and North Sea Midstream Partners. I'll put my teeth in. North Sea Midstream Partners. We've all been partners in the Acorn project in its current form since April 21, and we've been and continue to develop the Acorn project to move through to a final investment decision, into construction, operation, and then beyond. Acorn is actually one of the most mature and best understood UK CO2 storage sites. You can see on the map there the schematic showing how it's constructed from St Fergus out to the reservoirs of East May and Goldeneye. And is based off the coast of St Fergus in northeast Scotland and centred on the existing gas processing operations at the St Fergus terminal, which actually processes over a third of the UK daily gas demand, collecting gas that comes in from the North Sea. That terminal itself, you'll hear about that in a moment, are actually looking at capturing CO2 themselves and injecting offshore through the Acorn project. So the St Fergus terminal is a key part of not only our plant, but also a start of our emitter base. By repurposing the existing oil and gas infrastructure, and you see the metrics there in the green circles, both onshore and offshore, we're minimizing the new works we need to undertake. We're reducing cost and also reducing the project delivery risk, whilst ensuring the best value for our partners, but also probably these guys would say, most importantly for our investors. Acorn is specifically designed to service multiple emitters around the UK and Europe, and can rapidly scale up from that initial 5 million tonnes per annum, which we anticipate storing around 2030, to meet demand and store at least 20 million tonnes per annum beyond 2030 within the first decade. Initially, the reservoirs will have 100 million tonnes of capacity, but we will be looking at how we can extend and expand those going forward to meet the longer term life of the project. A differentiator of Acorn to many of our competitors is the proximity to the Peterhead port, which is close by, just south of St Fergus. So the Peterhead port is an active port that actually has been historically servicing the oil and gas industry offshore, but actually as that oil and gas industry in the UK starts to come off plateau, the port has been very quickly moving towards developing its own repurposing plan to become a key import hub for CO2 as part of Acorn. So it satisfies not only the Acorn objectives, but also the wider employment, longer term employment objectives of the port and the surrounding area. So by 2030, Acorn could include 9 different UK CO2 sources, including direct air capture technology, which is also part of the Storegga portfolio of services. Primary early sources of CO2 could include 2 of the gas terminals at the St Fergus plant, Segal, which is a Shell joint venture with Exxon, and Fuka, which is North Sea Midstream Partners, both of whom are partners in the Acorn project, so clearly have a real active part to play in that project. Additional to those is a large power station owned by Scottish and Southern Energy and Equinor, which is located right close to the port. That's currently developing a new gas turbine module that will have point source capture on, but will also be capable of fuel switching to hydrogen in the future. In addition, there's a new blue hydrogen plant supplying INEOS and PetroINEOS site at Grangemouth, which you can see on the bottom corner there of the schematic. And ExxonMobil and Shell have processing facilities at their Fife ethylene plant and Fife natural gas liquid plants. Collectively, all of these emitters together with Acorn are known as the Scottish cluster. Now, the inclusion of INEOS, Exxon and Shell is also bringing a novel bit of collaboration to the project, and that is supported by a wider repurposing of a main gas transmission network element that connects the central belt of Scotland with Acorn and is currently operated and managed by the national gas transmission operator, National Grid. So the aim is to convert one or more of those large feeder pipelines to supply CO2 to St Fergus, but also potentially take hydrogen away and supply that to Grangemouth. So I'm sure you can imagine the nature of those entities, private companies, oil and gas, and a national transmission operator. The collaboration challenge and the work that we're doing there is quite extensive, but it's been very successful, particularly in the last 2 years. Now, government support for developing CCS in the UK is very different to that in the US through the 45Q mechanism. In the UK and the EU, emitters already have to balance their CO2 that they emit by purchasing CO2 allowances from a liquid market, a liquid hub. So if you would like. Now the government is looking at supporting that by negotiating with the emitters, the large emitters you see there, to put in place contracts for difference, or CFDs, whereby the emitter pays to send its CO2 to Acorn, but the government subsidises the difference between the cost of sending the CO2 from emitter site to Acorn against what the emitter would pay if it had to purchase the allowances. And the objective or the tendency, the pattern at the moment is that those allowance prices are increasing in price all the time as part of the government strategy and as part of the economics of that. Those allowances have gone from €6 a tonne in the EU some 5 years ago to now over €100 a tonne. So emitters have to buy, for every tonne of CO2 they emit, they have to buy an allowance that matches with it. So that support is very different. It's on a revenue side rather than the tax credit side. Now, when the cost of those allowances exceeds the cost of sending the CO2 to the store, then the CFD principle is that those payments stop. And again, that's how we level out the process involved. Now, the process by which these CFDs are being negotiated is being driven hard by the government, working directly with the emitters. Some of these you will see in the cluster here that we're entering into those discussions. And the government has an aim to have 2 fully operational store clusters by the mid-2020s, 26, 27, and another 2 fully operational by 2030. And it's Acorn's firm intent to be one of those 4 operational sites. So in summary, Acorn and the Scottish cluster are an integral part of the UK's decarbonisation plans and are well placed to benefit from the government support. That process is set to continue, and we hope to be able to move that forward so we can move through the 3 phases of Acorn development you see there, 27, 28, 28, 29 and 30, so that we get to be one of those 4 fully operational sites by that time. In addition to the partners themselves in Acorn, significant expertise, resources and investment has been made by the emitters, INEOS, SSE, ExxonMobil and Shell, and we're really grateful for their support on that and their commitment. We believe the point Acorn has reached and now finds itself in puts us in a really good place, in a great position to benefit first from UK government funding, and then to work with our cluster partners to move quickly towards an FID for the Acorn cluster as efficiently as we can, and in order to be fully operationally ready by as early as 2028 if we can. So that's a really brisk walk through Storegga and the Acorn project. I'd now like to hand over to Elle, who's going to take over and take through how we've moved that little acorn and developed that little acorn, and how we're transferring our learnings and understandings and developing new projects globally. Over to you, Elle.
Thank you, Chris. So yes, I'd like to take you through some of the lessons that we've learned as Storegga through the years that we've been working in carbon storage. Now, the first of these is it's really important at early stages to develop a basis of design that covers the full value chain, starting with capture all the way through to storage. As geologists, I know this prevents you from wasting time spent finding the best store only to work backwards and realize that actually your project is uneconomical, or you have challenges in connecting that store to your emitters, or you don't, your store doesn't actually provide you the flexibility that is needed by your emitters. So if you aim to answer some of the questions like we've posted here, so what's the regulatory environment that you're operating in? How are you going to access your emitters and where are they located? What's the total storage that you need to service those emitters? What are the rates and the variability that you're anticipating, foreseeing? And how do they scale in the future as well? Will your business be importing emissions from elsewhere, or will it be internal? And finally, would you envisage a regional service provision like Chris described with the ACON project, where you're gathering emissions from disparate locations, or are you just servicing local demand for a specific emitter? And answering some of these questions plus more will really help you to identify the good stores that help you satisfy that basis of design, rather than searching for the perfect store that doesn't. Thanks, Chris. So the next one is not to overlook the saline aquifers. And we say this because back in 2013, the British Geological Survey, or the BGS here, conducted an evaluation to try and understand the potential of the UK offshore storage, carbon storage potential in the UK offshore. Now, the results of this formed the CO2 stored database, which is publicly available. And the results of that show that 88% of the UK storage is located in saline aquifers. Now, this represents a massive opportunity for carbon storage and pushes us to look beyond just depleted fields or structural closures for carbon storage. Now, this makes a lot of sense when you think of these large basins such as the North Sea and those that you have in Canada, where you have extensive reservoirs, and the lumps and bumps on top of those reservoirs constitute the locations of the fields. So looking out into the remainder of those reservoirs for storage is really where you can tap into that opportunity for saline aquifer storage. But with this opportunity does come the need to understand and utilize larger areas. So on the graph on the right-hand side, I'm demonstrating how for 100 million tons of storage, geological storage, you need an exponentially larger amount to store within saline aquifers versus depleted fields for the same reservoir and CO2 properties. So this means that we just need to take our understanding from oil and gas expertise and spread that in a more regional basis to try and tap into this saline aquifer opportunity. Thank you, Chris. Now, some of you may be aware the properties or the behaviour of CO2 is not necessarily straightforward, and so it needs to be considered at all stages in the facilities chain, right from capture all the way through to storage. Now, this is because when a CO2 transitions from a liquid to a gas, as you can see in the phase diagram here for pure CO2, it will do so instantaneously and also invoke potentially significant cooling. And I know that Alaskans are very familiar with cold temperatures, but we need to ensure that all the facilities chain is protected from these cold temperatures by managing the CO2 phase through the full chain. So, i.e., maintaining it within a single phase and preventing this change from occurring. Now, impurities will act to change the phase envelope and alter that slightly. And that will be important to understand as you bring different emitters into that CO2 stream and understanding how that phase envelope changes and the impacts of that. So there's a really good summary in a paper by Philip Ringrose, based in Norway, which covers some of these issues in a bit more detail as well, which I'd recommend. Thank you. Thanks, Chris. So the next one is when oil and gas benchmarks fall down when applied to carbon storage. So for those of you who've worked or are working within the oil and gas sector, you'll be familiar with the concept of a recovery factor. And that tells you the amount of, that basically tells you from the hydrocarbon field within the subsurface, how much of that can we get to the surface. So you won't be able to produce all of it. There will always be some amount left behind. And that recovery factor will tell you how much that will be. Now, that's a relatively understood factor, owing to the fact that we've got significant global experience in oil and gas production. And when you look to carbon storage, the carbon storage industry, there's a common misconception that the storage efficiency factor, which is used, is the same, is a proxy for a reverse recovery factor. And I'd like to talk you through why we believe that isn't necessarily the case. So, the definition of storage efficiency is the fraction of the available pore space that is used for CO2 storage. And it's impacted by a multitude of things, some of which are similar to a recovery factor. For example, your rock type or your development scenario, your development plan, sorry. And it really boils, but to calculate it boils down to this equation just here, which is the volume of CO2 stored as your numerator, your top number, over the pore volume available. Let's take each of these separately. So on the top, we have the volume of CO2 stored, and that will change through the carbon storage project from start of injection through to plume stabilization, as the plume migrates and finally stabilizes. And that may occur over hundreds of years, which is quite foreign to us working previously in the oil and gas sector or currently, those long timescales involved. Now, the second part, the pore volume available, is relatively subjective as to what you choose as your available pore volume. Will you take a cookie cutter of the reservoir beneath your plume footprint, or would you look to use your license area or another boundary as your pore volume available? So hopefully I've highlighted how there is an element of subjectivity that can enter into the storage efficiency factor. And currently where we're at with the carbon storage, this nascent carbon storage industry, is that there's a lack of standardization, meaning that it can vary wildly between, for the same project, the storage efficiency could vary wildly depending on the method used to derive it. And so, yes, it's just one thing to sort of watch out for and tap into a bit more detail, and also to make sure it's been applied to any storage resource estimate. Thanks, Chris. So the last one here is just a note of how we're all working together, and certainly lots of the carbon storage projects that we work on globally in Storega are either first of a kind in that country or first of very few. And so we're having to work through many questions for ourselves as project developers, but across multiple stakeholders. And these may touch on a wide range of topics. For example, what's the financial mechanism that Chris mentioned earlier, this difference between the UK and the US and what the approaches are. What's the regulatory framework that's in place, and what do we need to ensure that we're doing as a project developer? Some of the countries that we're looking at, that regulatory framework is currently under development, and some of and is kind of being worked through currently. What are the regulators that are involved within the carbon storage industry, and how do they interact with each other? How do you need to stay on top of keeping everyone informed as you're developing along the way? And also along with that is transferring the technical understanding as you develop your project further as well. So we would argue that early and regular regulatory engagement is really critical to ensuring successful delivery of carbon storage projects. And it can help to plan the project on paper and work through the entire timescale, because the answer that you give for year one may not be the answer that you would give in year three. And so that can really help you identify early pitfalls and also quick wins to the whole process. And lastly, just like to finish by saying that public outreach and stakeholder engagement is it's a key element to a successful carbon storage project. So really welcome seeing and being involved in webinars like this. So with that, I'd like to say thank you very much for inviting us to talk and look forward to any questions.
Thank you, Chris and Elle. Very interesting presentation, and appreciate that. Some questions are coming in. Are there any changes or upgrades required for the port location to bring in ships transporting CO2?
Actually, the port is pretty well sorted at the moment to take rather large ships. It's got a long draft. I think in the big draft thing on the slide, it said 14 meters or something. It's already well set up to take tankers up to 20,000 tons of CO2. It's actually able to take bigger ships than most of our competitors can at the moment. So the work with the port that we're looking at is focused really on the I can't remember the word, the pier that comes out. It's a very old loading port. It used to be used for loading and offloading ships. So we've done a lot of work on analysing the condition of that jetty. And it's the jetty that we need to do the work on in order to put the offloading booms for the CO2. But in summary, no, the port is pretty well set up to handle CO2 at the moment. We don't need to do that much, and it's well protected in terms of a breakwater and a wall. So we've been very lucky there. It differentiates the Acorn project pretty well.
Thank you. I think this question's for Elle. How do you estimate or calculate the storage efficiency E? How would you, for a new project?
Yeah, it's a really good question. So it can either be kind of taken as an input to a storage resource evaluation. So similar to a STOA, or oil in place calculation, if you're familiar with those. So then you would apply it as an input. So you take your rock properties and multiply them through with your CO2 density and then a storage efficiency. And there's literature. There's lots of examples within the literature which you can use to try and benchmark your site to try and select an appropriate storage efficiency. And then the other way would be through simulation, and then that would be kind of like an output, as it were. So you would model your plume migration and your CO2 injection, and then calculate that from your model. And one of the key aspects there will be to decide where you want to, that second part of the fraction, what you want to be your pore volume that you're measuring against. Will you take the whole pore volume of your model, or your plume footprint, or your boundary of your lease area? So yeah, input or output, but yeah, there's definitely some key things to think about along the way there.
Thanks, Elle. Here's another question. So what do you do with the rest of the wells in the lease where you're injecting CO2?
Elle, do you want to handle that?
Yeah, of course. So in projects that we're working currently, the legacy wells are, of course, a key component to the storage project that we need to consider. And each of those, we have now developed a good workflow of assessing the abandonment and the quality of the abandonment of that wellbore, and understanding its capability to hold back a CO2 plume if it were to come into contact with it. And so understanding that at an early stage is really important as well, actually, to understand areas within your lease area that you could develop, or areas that you'd want to stay away from with the plume. But there's also the element of pressure as well. So your plume, your pressure front, will likely go ahead of your CO2 plume. So you need to also understand the pressures that the legacy wells may see, even if it doesn't come into contact with your plume, in case you could start producing brine, for example, or hydrocarbon if it's still there.
Okay. Another question, and this we have a minute or two left. How much of the infrastructure for the project is new versus reused or existing equipment, like pipelines, wells, platforms, and compressors?
So in terms of the, we're going to be constructing an onshore set of facilities at St. Fergus. That will all be new. So the compression and conditioning will be new for the CO2. There's an existing pipeline that runs from Acorn to Peterhead Port that we may be able to use. We're looking at that now. But the main offshore pipelines that go to the old Goldeneye field and the East May field, they're still in situ. So when those producing fields were decommissioned, I actually was the asset manager for one of the companies that looked after several of those pipelines. We were looking at decommissioning those, and we didn't. We held back because of the government was asking to keep those out of the decommissioning plan. So all the wells and platforms have all been decommissioned for those fields, but the pipelines are still there. So we've done a lot of investigation, picking on the first one, the Goldeneye pipeline, and we've identified what we didn't need to do to put those pipelines back into service. It's not that much. So all that work's been done. So the main pipe, I think it was 420 kilometers of pipelines, are all valid there and ready to go and be used. So we need to drill new injection wells, obviously, for the CO2. Main pipelines are there, and we'll need to install some compression and conditioning plant on shore. The Feeder 10 pipeline, the National Grid pipeline, is a very big pipeline. The National Grid will operate that and upgrade that to be able to transport CO2 and H2. So there's a lot of stuff we're trying to repurpose. The more we repurpose, the better, for obvious reasons. So there's a big drive by the UK government to make sure that we repurpose as much of those pipelines as possible.
Okay. Thank you. Thank you very much, Chris and Elle. Very interesting presentation, and best of fortune with your project. It looks excellent.
Thank you very much.
Thank you.
All right. Now I'm thrilled to introduce our next presenter, Matt Federley. He is the director of the Cook Inlet Natural Gas Storage Alaska facility. And Matt lives and works on the Kenai, and these operations are literally close to home for him. Matt, can you take it from here?
Sure. Thanks. So yeah, I have a operations presentation. Cook Inlet Natural Gas Storage. We are a natural gas storage facility, but we're sharing it today to show you what an Alaskan CO2 storage facility may look like. I think Alaska's in a great position to take advantage of this opportunity. We have the reservoirs, trained workforce, knowledgeable regulators to safely store natural gas and CO2. Overview of the SINGS operation. We were constructed in 2011, commissioned 1st of April 2012, so just over 11 years. We have 11 BCF of working gas storage. We can deliver up to 150 million a day. We serve 3 customers, NSTAR Natural Gas, Chugach Electric, and Homer Electric. And we've worked hard to deliver safe, reliable natural gas service to our customers. On that note, all of our operations, including construction, we've only had 3 recordable injuries, and only one of those is a lost time, and that happened to be a slip and fall, but great credit to the workforce here in Alaska. So we're located here in Kenai, for those of you who don't know where that is. And what you're seeing here, this is the transmission pipeline system for South Central. Probably greater than 50% of the state's population lives within this, what you're seeing on this map here. The pipelines, as well as SINGSA, they're critical for providing heat and electrical generation to South Central. SINGSA, we're connected to 2 pipelines. This would be the A and B pipeline for NSTAR, as well as the Harvest KNPL pipeline. Gives our customers some flexibility on withdrawals. So for those of you familiar with Kenai, this is Bridge Access Road. If you've ever been dip netting, we're right next to the boat launch. So we blend pretty well. So you may not have noticed us, but we're here. So about a mile from the river if you were to head off this road off the top of the page. So just to walk you through the well pad facilities, this is a 7-acre site with about 5 acres developed, as you can see, and it's a DNR lease. We have 5 purpose-drilled storage wells here, storage injection wells. They're connected by a 6-inch lateral to a 16-inch pipeline. So I'm just going to follow that over there for you. We have a separator here. This is a vent silencer in case of emergencies. This is about 20 feet high, so if we had to blow down, this would vent the gas safely above any personnel that happen to be on site. Over here, we have some liquid handling facilities. A truck gives it some scale for you. And this is our MCC building, our electrical loads, whatnot. So pretty basic, the flow of gas here. On injection, we would come from below grade. There's a 16-inch that connects to the station. We'll look at that in a second. Comes up, goes through the separator. It goes through backward on injection. Goes into the 16-inch and then to each well. Each well has a choke valve so we can manage the flow individually. Typically on injection, they're all just wide open. So same thing on withdrawal. Flow is just reverse, except this time we go through the separator the correct way and knock out any free liquid, and that liquid stored on this tank for later removal. Station side of things, so we have the 2 pipelines I mentioned previous and the 16-inch that comes from the well pad. They all come over below grade. They come above grade right here by the measurement building. So I'll just walk through that. So this would be our meter. I'm sorry.
Can you right click on it and maybe turn your laser pointer on or something? We're not seeing your cursor there.
I'm sorry.
Oh yeah.
There we go.
Yeah, I can see it. Thanks.
All right. Well, I think the well pad was pretty basic. I think you could probably follow me even though you couldn't see the cursor.
Yeah.
Pretty much one line in and out. So this one will need the cursor. So yeah, all the pipes come in below grade and they all surface right here. You can't see it on the other side of this building here, but I'm just going to walk through. This is our measurement building. This is the cash register. This is how we impose our transport fees and whatnot. This is the manifold area. This is how, based on customer needs, we would either inject or withdraw gas. So we'd route it through the compressors or whatever's necessary. This is our compressor building. Inside of this building, we have 2 CAT 3608s with a dresser rand compressor. What you're seeing here are cooling fans. So it's just when you compress gas, it heats up. So a part of the process, we have to cool it back down before we send it on its way. This area here is our dehydration facility. So we have some preheat, a contact tower, and a triethylene glycol dehydration system. Vent silencer, strategically placed well away from where personnel would be in event of emergency. So off here, we have a communications tower. We run our own microwave network, a warehouse. And over here, this is auxiliary building, standby generator, air compressors, safety systems, and our office building. So I'll walk you through an injection. So as I mentioned, the KNPL pipeline. So gas would come through, we would measure it as it enters the station. The manifold area would route it to the compressors. We compress it, cool it, and then send it back below grade to the well pad. And that the well pad, like I said, simple. We go backwards through that separator into the 16-inch into each individual well. So withdrawal, the 16-inch comes above grade right here. We send that gas over to our dehydration facility. We preheat it first. Dehydration works best around 90 degrees Fahrenheit. Comes over to the contactor, and so our recent operation, the pipeline operates around 700 pounds or so. Our current pressure is about 1,500 pounds, so we cut the pressure right here. There's 2 pressure control valves. We cut the pressure, send it to the manifold, and direct it down whichever pipeline the customers have selected. So the difference, CO2 facility, you're not going to have a DI, you're not going to have a manifold if it's a one direction. Your compressor building, if you're compressing gas, could be similar size. Of course, the scope of the project would dictate all of this. If you were running centrifugals, probably much smaller turbine-driven centrifugal would take up a lot less room than this recip setup. But that's pretty much it. This is a 40-acre site with about 12 or so acres developed, and this area back here, this is we call this our pipe laydown area. It's just exactly what you see. We got lengths of pipe back here from construction still. I think that is about everything. We can come back to that in the Q&A if someone has questions. So what's the connection here? They share CO2 and natural gas storage. They share same operating engineering principles. Most of the equipment's going to be identical. Materials of construction, that will depend on the project. I've heard quite a bit about that the last couple days. The engineers will decide if it needs to be anything but carbon steel. The surface and subsurface regulatory requirements, they're going to be very similar, I believe. If you're operating a reservoir and wells, things are going to look very much the same. I'm going to go over some of that. We can use depleted natural gas reservoirs, so can CO2. Dr. LePain, he pointed that out yesterday in his presentation. And both require a trained and skilled workforce. And we have that here in Alaska. So, Frank, you talked about this earlier. We need a regulatory framework to move forward, and that's true. DNR, they'll need authority to issue leases and whatnot. But I'm going to talk about the AOGCC Storage Injection Order 9 and the PHMSA regulations in this presentation. There was actually 3 pages of regulatory items. I condensed it down to this one. But the PHMSA regulations didn't come around till 2018. Prior to that, we operated under the AOGCC Storage Injection Order 9. Since the PHMSA regulations came into play, SINGS has had several inspections, and we've had no sightings. I'd like to say we passed them all with flying colors, but unfortunately, they don't give you a flag or a ribbon when you pass, just when you don't do well, right? So I'm not going to get into differentiating between what are Storage Injection Order 9 and PHMSA. They lay over each other really. They're complementary. So I'm just going to lump them all together for this presentation. But reservoir oversight, it's all about integrity. We perform daily inspections. We shut in twice a year to gather reservoir data, pressure data. We have 12 or 14, I think it's 14 wells that penetrate our formation to a lower production zone that's still in use. So we monitor those wells for integrity. we capture all of our injection production. That's reported on a monthly basis as well as annually. And all that data is compiled, and a storage reservoir engineer reviews that data and produces an annual balance report. It's an integrity report. And it's important, right? You want the container to hold the product, whether it's natural gas or CO2. And it's not just from a regulatory side, it's important from a commercial side. No one's going to want to store their gas in your reservoir if it doesn't hold the contents, if it doesn't hold the product. Same story as we move on. So how do we get to the reservoir? We have to have a well. And so the business end of this happens to be well 3's storage schematic, or I'm sorry, completion schematic. So there'd be a well tree here. And so if you were injecting gas, whether it's CO2 or natural gas, they would come through the well tree, head right down the tubing, and down here to the perforation. So this schematic represents 5,000 feet, which I believe is roughly like 1.5 kilometers. So these perforations give us access into the reservoir. So the gas comes down, goes out into the reservoir. If it were fluid, it would act the same way. And everything above here is integrity. We're cemented. We cement the packer, 9 5/8 cemented to surface, 13 3/8 cemented to surface, and the 20-inch conductor. The regulations require that we have a modern construction. They'll do the same for CO2. They'll make sure the materials are correct. We have emergency plans, well MITs, that's testing that we do. So we pressurize this annular space. That's state witness. They set the parameters for the test. That ensures we have integrity. The packer, the tubing, the casing, the wellhead, everything's protecting the aquifers. We perform daily inspections, and then this device right here is our downhole safety valve. This is about 150 feet down, and the purpose of that valve is if the wellhead is here, it's missing, or the well tree. If that were to happen in real life, this valve would fail to the closed position and prevent the contents from the reservoir from coming up the wellbore. All regulated. So well tree, so where we left off from that schematics right here. So we have valves for isolation, for testing. This valve right here is the surface safety valve, and that also is tested and witnessed by the state, and it has the same purpose as the downhole safety valve. In the event of an emergency, it closes. Everything else we talked about, modern construction, this is a 5,000-pound wellhead. Emergency shutdowns for the surface facilities, daily inspection, valve maintenance. We have to ensure that these valves seal off the main, the side gate. And that continues on to the surface operations. So overpressure protection, we have relief valves. At SINGSA, we have 3 layers of overpressure protection, relief valves being the last one in line. Emergency shutdown, same thing. We have, valve maintenance. We have to make sure when we shut a valve that we seal the gas off. We perform corrosion inspections, surface, all the surface piping you see here, that undergoes corrosion inspection for external corrosion. And we also do internal corrosion inspections. Pipelines, we run smart pigs through them, and we actually measure the wall thickness with that device. The compressor shutdown you see in the lower left, that's our compressor. Behind it, that's in front of it is the driver. That's the CAT 3608. We have to test our overspeeds, high bearing temperatures, lube oil levels. Those are all shutdowns we have to test. Regulation even calls out we have to have security. We have to have fenced, lit areas that prevent access. And lastly, excavation safety. I talked about the buried pipelines, and you should see this 811 around town here in Alaska, or actually anywhere in the United States. And this is where we need the public cell. If you're going to dig a fence post or a mailbox or anything like that, if you call 811, 48 hours before you dig, we'll come out and mark our facility so you don't hit them. Keeps everyone safe, keeps service running. And last item, this isn't a regulatory item, but when we were obtaining our conditional use permit with the city of Kenai, and we're within the city limits, so they want to know, what are you going to do within the city limits, and can you do it safely? So we report to them once a year, as well as a DNR lease. We also produce a similar report for DNR. And a question was asked, what are you doing about seismic protection? And so the facility was constructed to withstand a 9.5 event. We poured tons and tons of concrete and rebore on these foundations here, but we didn't have a seismic shutdown and automation. So it was a great add to our safety systems here at CCUS. We bought 2 of them for each side, so they're independent. We got 2 at the well pad, 2 on the station side of things, and these are common switches. They're in every elevator, I believe, that the public has access to. So we have it shuts down and isolates gas at 5.5, and at a 7.5 on the Richter scale, we shut in and blow down the surface facilities. And that concludes my presentation. This is the CCUS crew. This is all of us, and our safety manager up in the top right corner there. So Frank, you're gonna probably have to come back on here and help me answer some questions.
Well, that's great presentation, Matt. Thank you for sharing about that and for keeping our heat and lights on here in Anchorage with smooth operating pressures on the pipeline. So thank you for sharing that too, especially on the earthquakes. Our first question is actually about earthquakes. And it was, how has CCUS performed during the earthquakes? Were there any impacts to the surface infrastructure or subsurface storage that you've seen?
So there hasn't been. We did shut down on the event. I can't remember the date, but it was like a 7.5, but it wasn't located right here. I can't remember exactly. So the way those switches are calibrated, the epicenter has to be directly below CCUS. So we're seeing the full event here at the facility. So that event a few years back, we did shut in. It did pick it up and we shut in, but we didn't shut in and blow down because it wasn't perceived here at the 7.5 level. And other times on smaller events, the compressors themselves have accelerometers for the shaft. So it's tracking bearing wear. And those actually picked up smaller events. They thought that the compressor was in some type of shutdown situation. So whenever there's an event, we have a procedure here. We do a full inspection. We inspect all our pipe clamps, all our foundations that are holding the pipe clamps down.
Thanks on that. So question from Don Reamer. How close were the pre-injection storage estimates to what actually is going in and stored and then being produced back out regularly? So the storage reservoir, I don't have the exact numbers off the top of my head, but the original production it started 20 something years ago
think it produced over 10 years. So we have a lot of information on the storage facility. The working gas content is only 11 BCF currently, and we filled that up with base gas or cushion gas. I don't know if that term's been used yet in the workshop, but that's essentially gas that's used to support the working gas. Working gas would be gas that's readily, you can readily inject it or withdraw it on a commercial basis. The base gas would be the gas that's pressure supporting that gas in the reservoir. So 18 billion is the number.
And it's behaving pretty as you expected, or any surprises?
No, it's tracked. Oh, sorry. Lights went out. So yeah, it's tracking the P over Z just like it should at this point.
So a question on turning around from injection to production of those wells. How long does that take, and how do you do that? So
most of that takes place in that manifold area that I was pointing out. The operator will typically get a several hour notice from the customers that they intend to switch their injections to withdrawal or vice versa. And the operator will make his way out to the station. It's a manual operation. We're an automated facility. Most of the functions here are controlled by a PLC, but that isn't one of them. So we have to come in, we have to physically switch some valves around, make sure all the pressures are right. We don't want to cycle valves with high differentials across them. And then if we're going on withdrawal, then they have to go over to the well pad and do some choke adjustments to the individual wells.
Okay.
Time frame, I guess it would just matter on what the pressure differences were and which direction we were headed, but fairly quick. They can get out here and turn that around fairly quick.
Okay. And I guess when you're on production, I was curious, you said you had to dehydrate the produced gas when it comes out. How much water is dehydrated out, and what do you do with that water?
So that water, I don't know if I have a exact volume of between what's produced, as a liquid and what was entrained. That just ends up in a total liquid number. But the gas is, it comes out of the ground fairly well saturated still. So we use a triethylene glycol dehydration system. We have, on the station side of things, we have 2 400 barrel tanks to deal with liquids. And then we ultimately send it on pipeline tariff, that tariff quality gas, at less than 4 pounds per million.
And what do you do with that water?
Sorry. So right now, sorry. Yeah, we dispose of that with Hillcorp has a disposal well just south of us.
Okay.
The grind and inject facility.
Okay. Question on kind of follow up on the earthquake question. What about tsunamis? Any concern with like water coming into the facility or flooding, that sort of thing?
We haven't seen any yet. We haven't seen any flooding or a tsunami, of course. That would have made the news. So we are close to the Kenai River. It is a concern, but I guess I'm not quite sure how to answer that.
So if you inject CO2 instead of methane, is there any differences on the treatment that you need to do on the injection or process lines?
Well, Frank, I think you're going to have to help me out with that one. You and I have had several discussions about that.
Yeah, I think the short answer is you'll have to dehydrate it before you compress it to a transportation pipeline spec. And once CO2 is dry, it can be handled quite easily with regular pipelines and common steel. So it's generally.
Yeah. And I think, on that note, I think transporting gas and inspecting pipelines, we're well prepared for that as an industry. The smart pig technology it's really incredible from where we started years ago. All we had before were gauge rings, right? So,
So there's a question here. What is the CCUS round trip cost in dollars per MCF for storing gas?
I don't have any of the commercial information here with me today. Sorry.
Okay. Can you talk about like the RCA and how all that is, how you work with the RCA for?
So yeah, CCUS is a regulated facility. So we also, they were on, I believe, that slide for the our regulatory framework slide. So yeah, that they set the rates. We have to go in every year, set forth what it costs us to operate the facility, and then they set our rates, and the customers have a chance to, intervene or cheer us on or wherever they see fit.
Okay. So has the CCUS facility ever been like full? And is it full now?
Since becoming storage, it hasn't been full. We came close last year. We came to about 10, I think we got to 10.6 BCF. And that's just our working gas, of course. And then you add the 7 of, saving electricity. So the 7 base gas and the working gas combined to make the 18. We got to about 10.6, and this year I think we're probably gonna fill her up this year. It's totally dependent on the customer's use, of course. We don't control it. So it's April, and we've got around 8 BCF in the field now, so only 2 BCF to go to get to 10 and a half. So I expect we'll see 11 this year.
It's nice to have a full tank. So, and I guess kind of looking forward, is CCUS going to stay operational for a long time? How long do you expect it to operate or last?
Well, as long as there's a need for natural gas storage, I expect we'll be around. My previous employers, I've worked at facilities that were built in the 50s, and they're still running. So, these are built to last, and they're maintained that way also. So I expect things to be around for the foreseeable future anyhow.
And of your operating equipment, how much of that is new versus reused? What happened? Were any of the original wells from production used as injection wells, or what's the story there?
So there was only one well drilled into the Sterling Sea sands, and that was well 6, and that was used to produce that was Marathon did that, and they used that one well to produce the entire contents. About 10 years, and so that well is plugged back. It's still the surface facility exists, so it's plugged back, and everything at Sings is brand new. The wells were purpose built, as well as the surface facilities, and that's why I believe that anything that is CO2 wise greenfield, it'll look very similar to Singsa. That's just the modern construction.
Okay. So question here on LNG. If South Central starts importing LNG, how does that affect Singsa operations?
Well, unloading ships in the summer that give our customers somewhere to store that gas. So yeah, I see the customers utilizing SINGSA just as they do today.
Okay. And was it difficult to get this reservoir permitted as a storage facility?
So I came on during construction. So I believe that effort or campaign probably started a year in advance or so. I don't recall, so I wasn't intimately involved with the permitting process, but I don't recall a whole lot of griping at the office. So I think it went fairly smooth.
That's good to hear. And thanks for sharing the detail on the regulations and management and operations of the SINGSA facility, Matt. That was very enlightening and a great analog for potential carbon storage operations here in the state. Looks like a beautiful facility, actually, really first class stuff. So thank you. And with that, I would like to welcome and introduce our final presenter for the workshop. And that's Justin Seavey. Justin is a senior engineer with Usabelli Coal Mine, and he'd like to share some discussion about CCUS and the coal sector here in Alaska. So it's been a pleasure getting to know and working with Justin in carbon capture, and I'll turn it over to you now, Justin, for your presentation.
Thank you, Frank. So again, my name is Justin Seavey. I'm Senior Projects Engineer for Usabelli Coal Mine. And just a little background on our company. We're the state's only operating coal mine, and we've been in operation since 1943. So we're celebrating our 80th year of operations this year. One of the things that happens when you've been in business for 80 years is that we are a fourth generation Alaskan family owned company. We are very active and involved in our community. And in interior Alaska. These are our family and friends and neighbors in our backyard. So the Usabelli family, through the business and also through the Usabelli Foundation, is very heavily involved and invested in the interior Alaskan community. We serve all of the power plants in the interior, all the coal-fired power plants. There are 6 of them. And something that's unique about our coal is that it is ultra low sulfur. It is some of the lowest sulfur coal in the world, which gives our power plants a little bit of a leg up on the emission profile as it pertains to SOx. And we're interested and we're studying carbon capture and storage as a way to meaningfully decarbonize the interior Alaskan energy grid. And so when we talk about the grid, for us, a very large part of talking about CCUS in the interior is talking about the infrastructure. Whether you are talking about adopting electric vehicles and you're putting in charging stations, whether you're talking about improvements to the grid, either through expansion or efficiency, when you're talking about any of these things, you're talking about an infrastructure project. And from our point of view, one of the things that we're looking at pretty heavily is that we don't have a lot of infrastructure. Alaska has some of the lowest infrastructure density in the United States. Getting new infrastructure is difficult in general, but especially right now in terms of funding, in terms of permitting, those sorts of things. You know, we need to make the best use of the infrastructure that we have. Demand for energy is only going up. And so as that demand increases, the infrastructure that supports it needs to expand, whether that's capacity, whether that's efficiency, the infrastructure needs to expand. And that's a pretty difficult thing to do without leveraging all of the infrastructure that you already have. So we kind of see carbon capture and storage as a way, if we can convert the existing coal fleet in the interior as a way to meaningfully decarbonize this grid, but use the existing infrastructure. We have a security of supply. We have an established distribution infrastructure for the fuel. We have all these things. We have the next 100 years of coal under permit. So rather than kind of reinvent the wheel, let's modernize that wheel and let's soup it up and let's turbocharge it and move into the future. So as I said, there are 6 power plants in the interior. In total, we have about 165 megawatts of coal-fired power generation. The largest single plant is 50 to 60 megawatts. Something that's really interesting about the generation sector in the interior is that 90 megawatts of that cogeneration, 4 of those 6 power plants are cogeneration plants. So not only are they producing electricity, we're actually reclaiming heat off of the process and using that for indoor heat. The Aurora Energy Power Plant in downtown Fairbanks heats most of downtown, and Fairbanks, in interior Fairbanks. The plants at Fort Wainwright and Eielson Air Force bases also heat those military bases. And then the plant at the university also heats the campus. So cogeneration, really, it's unusual to find this concentration of cogeneration plants in one area, but it really maximizes the benefit of the fuel source. You know, we're getting 2 for 1 on the carbon emissions, but we're also getting everything we can out of that resource. One potential downside to that is it does make centralization of that problematic. It's difficult to have one giant power plant that feeds everything. That's why we have 6 smaller ones. But one of the reasons that we're interested in carbon capture is because if we were to replace the electricity generation with renewables, you're addressing the electricity load, but you're doing nothing about the heat load. And you're actually making it worse because now you create a need for hundreds of new distributed point sources all over Fairbanks. There's hundreds of buildings and homes that would need their own boiler, their own heating system, and they would be burning fuel oil to do that. And so we see carbon capture as a way to address that need as well. So again, as I mentioned, we have 6 power plants, but in total, 87%, almost 90% of the energy in the interior comes from fossil fuels. 43% of it, of all the energy in the interior comes from coal. Coal is the lowest cost fuel source. But if we're going to talk about meaningfully decarbonizing interior Alaska, it has to start with decarbonizing fossil energy, and carbon capture, utilization, and storage is a pathway to that. In total, the coal-fired CO2 emissions in the interior are about 4% of the state emissions, so it's maybe not as big as some of the other applications that are out there, but interior Alaskan families are already paying twice the national average for their energy, and so anything that we can do to maintain and hopefully improve on that while also decarbonizing is something that we're really, really excited about. So how can carbon capture apply to interior Alaska? One of the things that is really interesting is the scale. We're not talking about the scale that a lot of carbon capture and storage projects are looking at. We're really pretty small. If you were to take all 6 power plants combined, that's a quarter of the size of some of these projects, such as Project Tundra in North Dakota. We mentioned the heat loading, which is really kind of an under-addressed part of energy consumption, but it's certainly outsized in interior Alaska. But because of our scale, most of these technologies, most of the demonstration projects for technologies that are already out there are full-scale solutions for us, which does a couple of things. It makes us pretty attractive for some of the federal funding under IIJA or some of the other programs. It also makes us a candidate for some of the new and emerging technologies, whether you're talking about maybe a solid sorbent-based capture or even a membrane-based approach. You know, some of those technologies that have been demonstrated now but are working and trying to figure out how to scale up to reach the size of a project like some of the projects that are out there. We don't need that. We're talking about retrofitting, 25 megawatt to 50 megawatt generating units. And a lot of these technologies have already been demonstrated at that scale. We also, again, see this as a way to address the heating component and really to address the reliability component. One of the most important things for us is that energy remains reliable in addition to affordable in the interior. When it's 30 below and your heat goes out, that's a problem. Or maybe your heat doesn't go out, but the electricity goes out. Most heating systems are run off the electricity. So we're really interested in taking a methodical and thoughtful approach to this, but it's something that we're very excited about. And so both the Department of Energy and the state of Alaska have recognized a need for a regional solution for us for the interior specific to our needs. And you're starting to see that with some of the federal programs that are coming out, as well as some of the legislation at the state level. We've been actively involved at the state level up to this point, and it's something that we're watching very closely. More broadly for the state, carbon capture technology is really an enabling technology for Alaska and for our economy. Our economy is built on fossil energy. And so if there's a technology that enables fossil energy in a way that's meaningful in the context of managing carbon emissions or decarbonizing, then that's something that's quite attractive. More than that, Alaska's uniquely positioned to be a potential leader in carbon capture and storage because of the identified world-class storage in the state, and also some of the unique ways that the state manages land bypasses some of the land management issues that you can get into when you're talking about managing a potential storage facility. But so we're taking a slow but cautiously optimistic approach. We want to make sure that we do this the right way. Like I said, this is our backyard. These are our friends. These are our neighbors. We want to make sure that we learn everything that can be learned about the projects that are out there, how it might apply to the interior, how we can tweak on it, how we can make it better. We already have some of the most modern coal-fired power plants in the country in our grid. And so we are already doing a good job cleaning up the coal-fired energy sector. We want to do everything we can to continue that progress. And so at that point, I've really kind of addressed everything in my notes, and if anybody has any questions, I'd be happy to answer them. But thank you guys very much for listening to us.
Thanks, Justin. Really appreciate you sharing your perspective, and let's move into some questions and answers. I guess one question is, how could coal-fired power generation work with renewables? You mentioned, the times when the wind's not blowing, sun's not shining. Can coal-fired power generation provide that baseload power?
Very much so. And I want to be clear and say that we're not anti-renewable. This is an all of the above kind of solution. This is not a zero-sum game. And with the projected increase in energy demand, there's enough new demand to create generation for just to keep up with. And so coal is really good at providing that steady, reliable base load, but we can't deal with with swings in usage during peak periods. And so that's where coal-fired power plus renewables or some other ancillary services working together can really address those needs.
Okay, great. So actually, I just recently came across a study that the governor commissioned in 2021, a renewables power study from the National Renewable Energy Lab for the Alaska Rail Belt and South Central Power Grid. And that was published in 2022. And it found that it was required for energy reliability to retain at least 80% of the existing fossil energy power generation to maintain reliability in those times. So seeing that as a fossil energy will remain a big part of our energy security for the state.
Unquestionably. And I would say that the U.S. Energy Information Agency, even in all the projections that are out there going out to 2050, fossil energy is still projected to be 40 to 50% of the grid, nationwide. So that doesn't mean that we shouldn't be working on ways to meaningfully decarbonize that grid and contribute to the solution. And so that's one of the things that we're very interested in. But then even more specifically, more locally for the state of Alaska, you're exactly right. Retaining that infrastructure, not just from a reliability standpoint, but also just from a practical standpoint, is really important. We need to be expanding our infrastructure, and that's really hard to do if you're going to start over on 80% of it.
So we've got a question that came in on coal reserves. So the question is, how many years of coal resources at the current rates can Usabelli provide? And is there a plan in place when the coal runs out?
So I'll answer that in two parts. I think I mentioned we have the next 100 years of coal at current production rates under permit right now. They're at the mine. And with our newest and most modern mining area, it's really kind of open-ended. There's lots of room for expansion. I guess the short answer is no, there isn't a plan for when the coal runs out, because that's going to be well past any of our lifetimes.
100 years, five generations. So, and that's with current approved. That's a long time. It gives us some running room on this.
Very much.
I guess we heard from Carbon Clean yesterday discussing their modular equipment design. Would that equipment be viable for the interior? Or I guess we heard about the boundary dam process used at the Saskatchewan coal-fired power plant there. Could either of those work for the interior?
I think potentially they could. I don't have any information to say that they couldn't. One of the things that we're looking at right now is we've kind of started doing research by plant, on what potential technology solutions on the capture side might be most appropriate, because we do have kind of a range within the grid. We have probably the newest and most modern coal-fired power plant on one end, and then we have some much older technology on the other end. And each of these plants has their own quirks, the way the boiler works, the way their controls work, the way they're tuned to burn the coal. And so it's not exactly a custom designed solution, because there are starting to be some of these solutions, such as boundary dam, that are becoming more widely applied. But the tuning of those solutions is going to be a little bit custom. So one of the things that we're considering doing right now is looking at kind of a comprehensive plant by plant study, to see what sort of technology solutions by plant might be the most appropriate, so we can look for synergies there.
Okay. And Usabelli is the supplier of the coal in the state. that you're a common thread between all 6 of these operating plants. I guess I don't want to put you on the spot too much, but I guess are the coal-fired power plant owners working to investigate carbon capture, or is that really viewed as kind of ask Usabelli to research that on their behalf? Or
Well, so we very much believe that it's a partnership. And so we have been engaging each of our customers, the power plant owners, on this. And they all have their own unique interests in carbon capture and storage. You know, this really is very much a partnership. And we want to make sure that we're engaging the entire community in the development of an interior carbon capture project rather than developing the project and then coming to the community with it. And so that's a very, very important part of what we're doing right now, is working with, whether it's the university, whether it's the military power plants, whether it's Aurora Energy downtown, you know, finding out what their interests are, you know, how specifically they are interested in carbon capture, and what we can do to work together on it.
So I guess kind of as a follow-up, we've seen some recent announcements about the Healy 2 unit and Fort Wainwright that they're looking to maybe switch fuels, or do you think carbon capture and storage could change those decisions or affect the trajectory of coal-fired power in the state?
That's difficult to say. You know, I certainly can't speak for those other organizations. I think if you're talking about decarbonization, if decarbonization is the goal, if you're just looking at switching a fuel source, then you're still eventually going to be looking at carbon capture and storage, you know, one way or the other. Maybe the specifics of the process are different. And I think from our point of view, there's not necessarily a need if you're going to end up in the same place anyway. There's even some potential advantages to coal-fired CCUS, depending on the application. Some of the capture costs can be lower, and so there's maybe some opportunity there as well. We have not spoken with either of those 2 power plants on carbon capture and storage in the context of those specific plans. We haven't got to that level of detail with them.
Okay. Let's see. So Dr. LePaine yesterday talked about the scarcity of subsurface data available to characterize storage potential in the interior. I mean, and what, if anything, should we do to address that data shortfall?
Well, I would say that you've kind of hit there on one of the biggest opportunities we have to move the ball in this context. Is, you're exactly right. There is not a lot of readily available data, just because, quite frankly, the amount of oil and gas activity in the region is lower, and a lot of this data is collected in the process of, ongoing oil and gas activity. There have been regional studies that have been done that have identified, as recently as 5 years ago, that have identified potential storage in the area that far exceeds what we would need. If 3 to 5% of that potential storage in the interior was to actually prove out, that would give us enough storage capacity for the next 50 to 100 years. But there is a lot of work that needs to be done to collect that data, to identify the sites that go to the next level of study for characterization. EPA Class 6 permitting is a very involved and data-intensive process. And so that's very much on the critical path for an interior carbon capture project.
Okay, that's great. Good to hear. And I am familiar with the research underway at the University of Alaska Fairbanks on a pipeline transport analysis. Dr. Zhang's leading that effort, and they're studying the various basins, interior Cook Inlet and North Slope, and looking at the I guess, feasibility of pipelines to interconnect if you installed and maybe do like a hub and spoke kind of a concept for that. So Dr. Zhang, we're looking forward to the results of that analysis.
We are as well. We're very interested in the carbon hub and spoke sort of approach.
So I guess kind of bring it back to the theme of the workshop here. Do you see like carbon capture as a myth, or is it a real possibility for us here in Alaska?
I think that that's a really interesting question. I don't see it so much as a myth, but there are certainly carbon capture projects around the world that show that have become reality. I think as it applies to Alaska, there's a lot of hard work to do, and there's a lot of potential off ramps. You know, if this is something that we're going to do, we want to make sure that we get it right, and that means, you know, if you get all the way down to this stage of the technology and you find a problem that isn't right for our application, then maybe you got to circle back and maybe hopefully not start over, you know. But so now we're talking about time horizons. Is it realistic to think that we're going to have a project like this in the next couple of years? Maybe not. But given enough time and given the uniqueness of our application, I think it's very much, it has the potential to become reality if I'm not sidestepping that too much.
Oh, I think it's a fair answer, and appreciate it, and appreciate your willingness to step forward and share your thoughts on coal-fired power generation and carbon capture in the state. Appreciate everything you're doing to keep the heat and lights on for us.
Well, and I certainly appreciate you and ASAP and the university for having us, and for listening to me. And again, thank you guys very much.
Okay. Well, that brings us to closing remarks for the workshop here. And I'd like to thank the moderators and the presenters, the University of Alaska Fairbanks and ASAP for hosting this virtual workshop. And thanks Sarah and her team who managed all the workshop logistics. Great job on that. So, and to close, I'd like to summarize some of the things we've heard in these 2 days workshop on carbon capture. We heard from Ruth Ivory Moore at the Global CCS Institute, and she shared yesterday a CCUS 101 discussion and their view that CCUS is critically important for reducing CO2 concentrations in the atmosphere, in that some processes, industrial processes that are really civilizations founded on, like cement manufacturing, that can't be done without generating some CO2. And so point source capture and storage, and also direct air capture, are going to be needed to decarbonize those operations and take care of that in the long term for the future. And Ruth also shared that the International Panel on Climate Change did a study that found that achieving sustainable clean power, that cost would be more than twice as expensive without carbon capture. And so carbon capture, while it is costly, it's a very efficient and cost-effective way to leverage the existing infrastructure to provide clean power in the future and help us in our transition to a carbon net zero. Then we heard from Laura Brannon from the Nature Conservancy, and they shared also that CCUS is a needed part of the overall sustainable energy plan to achieve a lower carbon future. And Carbon Clean, they shared their technology for carbon capture, which is modular and scalable from as small as 1 ton per day capture to several thousand tons per day on a major industrial scale. And it was interesting to see, they showed like ongoing proven operating technology installations that they have going on and being installed around the globe. Dr. David LePayne would be a great person to have on your team if you want to do any geological work. He reviewed the geology of Alaska and the potential of Alaska basins for storage of carbon. And in summary, the North Slope and Cook Inlet have lots of subsurface data from the commercial oil and gas operations, while the interior has less data, generally speaking. And his presentation, he shared a ton of info, and I recommend reviewing his presentation later if you have the time when those presentations will be posted to the workshop site. So Nick Fulford from Gaffney Klein, he reviewed the business case for carbon capture and some of the macroeconomic drivers, what he termed the carrots and the sticks that are in place to incentivize commercial carbon capture and how that's evolving over time. So great presentation there from Nick. And then yesterday wrapped up with Richard Suggs from the North Dakota's Carbon Injection Management Regulatory Agency. And he shared that a project application takes years to prepare and a year almost to review, and it can be as many as 1,000 pages long. And that detailed geology and subsurface understanding is foundational for a successful project. He showed some great summary slides of how the injection process is forecasted to behave, and then it's monitored and tracked over time. So excellent presentation and really crystallized a lot of things on the regulatory side for us. Today's presentations included Iceland's growing experience with direct air capture and the use of geothermal energy in supporting carbon capture, and also the conversion of CO2 into solid rock by injecting it into basalt. And that's definitely a technology to watch and pretty very interesting. And then Rand shared the Boundary Dam coal-fired power plant, which has captured over 5 million tons of CO2 so far and stored it subsurface safely. And he shared kind of some of the incentives that are in place in Canada and compared them to the ones in the United States that make carbon storage economically viable. We heard from Acorn Project in Scotland, which is going to start up in 2028 as a major CO2 storage transport hub and reusing depleted gas fields for CO2 storage. And finally, we brought it all back to Alaska with Matt Federley sharing the ongoing operating gas storage project for natural gas on the Kenai Peninsula, SINGSA. And Justin Seavey at Usabelli Coal Mine shared his options and thoughts for carbon capture and on coal-fired power plants. So great set of presentations, and really appreciate everyone's participation. A big thank you to the presenters for sharing their work and their viewpoints, the moderators, the University of Alaska Fairbanks and ASEP, and a huge thank you to all of you for joining us at the Carbon Capture Sequestration virtual workshop, The Myth and the Reality, which was sponsored by UAF and ASEP, the Alaska Center for Energy and Power. A recording will be available shortly at the website alaskasustainableenergy.com in the near future. Please check back in for more information. And as a follow-up, we're going to be sending out a short survey from the workshop, and we'd love your feedback. You can access this survey by scanning the QR code on the screen now, and we'll drop it into the chat also. And anyone who completes that survey will be entered to win a 3-day conference ticket to the Alaska Sustainable Energy Conference in May. And you can attend either in person or virtually. So please take a moment to submit your response on a short survey. That'll help us improve our future workshops. So we appreciate everyone, the moderators, the presenters, and all of the attendees. Great questions. And we invite you to attend our third and final virtual workshop, Energy Storage Beyond Lithium-Ion Batteries, which will be held on May 9th and May 10th. And we hope to see you all at the Sustainable Energy Conference at the Denaya Center in Anchorage, May 22nd through May 25th. We do have in-person and virtual tickets available for that conference, and we hope you'll consider joining us for that. Those can be purchased now for the event at alaskasustainableenergy.com. Thank you all very much, and I hope you learned something these 2 days and appreciate a little better what carbon capture might look like for Alaska and for the world. Thank you all and have a great day.